Already come?
That's like he will be coming soon.
Will be coming. So Professor Kamath is
sometime back he mailed me and made sure at what time he's supposed to deliver his talk.
Okay, okay. Now it is chaired by the chairman.
Dr. Asha Kamath is that.
I'm Professor Kamath. Yes.
Yeah, she's coming. Now it is 9 o'clock. She may reach any time.
Anytime, okay.
He had to travel all the way from Mangalore to reach Manipal.
Okay, okay. Yeah, it's great. Today in the talk I'm going to explain, how the AI research can be taken by the Manipal Institute itself.
True. In fact, it is a very useful topic for students as well as faculty members.
Correct. There is a lot of, that's what Dr. Haslett, you saw in the email he wrote.
Yeah, right.
That he liked the concluding the remark because the new alternative for the AI, because a lot of hype is there on the AI. People are misusing.
Yeah, that is the hot topic of the day, no?
Correct. In fact, that's the reason government of India also, I mean, their committee, one of the committees, 18-member committee, they formed and they put me as a domain expert for the AI. So that's what I suggested them. It's not that S-manship. I don't like to be, because they put me in the committee means that should be useful for them, not to any benefit for me. I mean, I don't gain anything by being a member. So I want to be candid in the comments about the actual implementation of AI, because if India publishes 10,000 papers a year on AI, but none of the papers are contributing for GDP towards AI, then these 10,000 articles have no meaning for India. Isn't it? Because AI is not just like a pure maths, or AI is not like a chemistry. AI is not, it has to be shown in the ground.
Right.
So that sense, today I'm going to talk on those things. Yeah, anyway, other audience are there, so introduce the topic.
Yeah.
You had
we missed the beginning part itself yesterday.
Correct. Beginning. So I will highlight the beginning again today. So do you remember whether the stock exchange thing I explained was part of the was audible, or that also missed? Or you not?
Yeah, missed it. Right.
Missed it. Okay. But the virus research part was seen by all, isn't it?
Yeah. Right. Anyway, that can be repeated now.
Sure. Thank you.
So you will get about 50 minutes, including discussion at the end.
So how much time I have?
The same, almost same as that of yesterday, about 40 plus 10 minutes.
No, I thought total me and Dr. Haslett together it's 1 hour, isn't it?
Yeah, I agree. For you it is 40 minutes plus 10 minutes. For again for him it is 40 minutes plus.
No, I thought together 1 hour.
No? Yeah, you are correct.
Together 1 hour is high. It's not half an hour, 30 minutes each.
1 minute.
9:10 to 11:10.
9:10 to 9:50 one, and 9:50 to 10:40 another.
Oh, I see. Okay.
Yes,
okay.
40 minutes altogether, including discussion.
40 altogether. Okay. Okay. Sorry, I misunderstood. My fault. This is also an issue. Nighttime. A whole day you work in the office. That alertness also one has to be. This thing. You're right.
Many times I go wrong. I get confused. I fail to recall some of the things.
Yeah, I know it's not easy.
Most of the time I don't commit. Dr. Asha Kamath is here.
Hello.
Hello, namaste.
Namaste. How are you?
Doing very good, ma'am. How are you?
Good, good.
Yeah, you traveled from Mangalore. That's what Professor was saying.
Right.
Dr. Asha, you must have got the message from KRMS.
Yes.
Yeah. Professor Arni Rao, he will be delivering his talk again.
Yeah, I got it yesterday itself.
We are happy that He could take all the trouble and join us again and deliver it for the benefit of audience and students.
Today there is no echo.
They have taken now. They have become somewhat expert now.
Yeah, the moderators they can mute all or they can unmute all depending on their control.
Yeah, yesterday they have noted that it is not. I mean, audience were not muted.
Correct. Today also I don't have permission. Right now I see I don't have permission to share the screen.
Is
Maybe
it?
they will be given soon.
There's no chat option.
Chat option is not there. You're right. Also, the sharing screen is also not there.
I don't know. There is some problem with our MS Team thing. I think. I don't know.
No, I think I think the moderators can permit instantly.
The organizer has to enable it and make him as a presenter.
I just get it. I'm in different room now.
Sir, it is enabled. Please try if you can share it or not.
Yeah, now I can share, ma'am. Thank you. Yeah, now the option has come. Thank you. Professor Haslett also there?
Yeah, he's the next speaker after you.
Correct, yeah. He is muted.
Yeah, no, I'm here, Annie. Yeah.
Oh, hello, Professor Haslett. Yeah.
I'm just. Oh, I can put on my camera too if that helps. Yeah.
Good to see you.
Yeah. So with my talk, I don't need to. It's already pre-recorded, so.
Oh, it is recorded already?
Yeah, so I think that should be simpler.
Yeah, I was just telling Professor Prasad, that you are the comments were very thoughtful, and then you support the idea of it's a lot of hype is there, and
certainly is. Yeah. Well, I think it's. I think that there's a sort of universal phenomenon that the people who are that often people who want these systems don't understand what they are or their limitations.
Correct.
And they're being sold it. So
exactly.
Shortcomings are not mentioned.
Good morning.
Morning.
Shall we start? 1 minute. Anything urgent? Quickly. Good morning. Tell me. Yeah, now we are about to start a morning session. Tell me. Yeah, okay.
No, sir. Okay, sir.
Yeah.
Yes.
It is Dr. Susmita's phone. Anyway, it's taken care. Yeah, now time is about 9:10. Shall we start? Let me say good morning to everyone very formally.
Yes, sir.
So again,
Yes, sir.
You don't feel this thing.
Raksha?
Yes, sir.
Raksha, you put off your mic.
Yes, sir.
I think the administrator can unmute, can mute all.
Is it all right? Okay. Am I audible now?
Yes.
Okay. Let me say good morning to everyone formally. Now, Professor Arne Srinivas Rao and Professor Asha Kamath and Professor Steve Haslett are there. Yesterday, due to some technical glitches, we couldn't transmit Professor Arne Srinivas Rao's talk correctly. He kindly agreed to deliver his talk again today. He's talking, sorry, sorry. He's taking all the trouble in delivering this talk, and this is very late midnight for him. And Dr. Balakrishnan, he couldn't join us due to his poor health condition. In fact, he was recovering very fast. Still, he tried his best to join us and preparing his talk. Unfortunately, his physical condition did not allow him to get ready for today's talk. So we will continue without him, and we'll have Professor Arne Srinivas Rao in his place today, and he's taking all the trouble and joining us and delivering the same talk. I'm sure that students and other participants will benefit from his talk. Raksha, over to you. Raksha.
Said, hello, am I audible?
Yes.
Yes, okay. So as Professor Prasad already said, Professor Balakrishnan was supposed to join us. He is a distinguished university professor at McMaster University, Ontario, Canada. Recently, he was awarded as a fellow of the Royal Society of Canada. He is a main force behind us in ALAPS 2020 and IWMS 2021. He intends to give live talk on some interesting features of linear prediction. Unfortunately, he could not join us due to his health condition. So instead of his talk, we will have a lecture from Professor Arne, who will be delivering his talk again on the topic exact deep learning machines, artificial intelligence, and deep learning methods. Following his talk, Professor Steve Haslett from Massey University, New Zealand, will deliver his talk. Professor is a fellow of Royal Statistical Society, a chartered statistician from UK, and formerly president of New Zealand Statistical Association and managing editor of Australian and New Zealand Journal of Statistics. Professor has been a statistical consultant for over 30 years during his time. His areas of interest are mathematical statistics, medicine, health science, psychology, human development, political science, history, etc. So today he will be delivering a talk on the role of block diagonal matrices in conditions for equality of blues in linear models. We are very happy to have both of you here. I now request Professor Asha Kamath, Associate Director from Prasanna School of Public Health and Head of the Department of Data Science, PSPH, Mahi Manipal, to chair this session. Over to you, ma'am.
Thank you, Raksha. Good morning, good evening, good afternoon to all in your respective places. Welcome you all to this session. And as you all know, machine learning and artificial intelligence buzzwords of the present era. We have a very proficient personality to have this, roots of these discussed in the forum today. So we have Arne Srinivas Rao from Medical College of Georgia, Augusta University, USA. I think I should not be eating away any time of his. Over to you, Professor Arne.
Okay. Namaste to all. Thank you, Professor Kamath. And I'm really honored to repeat my talk again. And I want to thank in this connection Professor Prasad and Professor Haslett for providing the slot. And it was, I'm really thankful for them for their kind invitation again. And I also want to pray, for a quick recovery of Professor Balakrishnan. Yeah. And yeah, it is a wonderful opportunity to speak to you all. As I mentioned yesterday, the theoretical foundations, I have been working on the theoretical foundation of AI. And one of the major contributions of me in the past 3 years was, how best AI, how mathematically AI can be well structured. And given the situation, I have been arguing that the field of AI is more closer to the mathematics than it is to the computer science. Computer science comes later when the foundations are well set on the ground using the mathematical principles, not even statistical principles. So that that kind of clarity that I have been presenting at various places, and then that's how the concept of exact deep learning came up through my research. And then after that, I showed how this exact deep learning can be applied for the treatment for the infertility clinics. And later, as soon as the COVID came, I demonstrated that this kind of applications can be used to identify the COVID-19 patients. And as I mentioned, that was the first article worldwide to get published. And then later it was adopted as various, it inspired for various other apps, including the Arogya Setu, as it was discussed. And I want to thank also Professor Haslett for appreciating, based on yesterday's talk, whatever he could understand from the technical glitches. So let me start my slides. Yeah, that's the title. Already you heard the title. And I want to thank my recent funders, NSF, and I'm going to ask more funding from NSF for performing more experiments and more foundations on AI soon. And the outline of the talk, if you see that, I will explain again the foundations of AI and exact deep learning and deep learning. And exact deep learning is a new word, new phrase that I coined. And the institutes like Mahe can take the initiative and then see that practically they test the implications of AI in a realistic way, not just publishing articles. The publishing articles are important also, but unless this kind of AI technologies are being tested on the ground by collaborating with the industry or within their own interdisciplinary faculty, bringing a smallest of the small AI machine is more important than even publishing 1,000 articles on AI. So in that sense, I think the government of India and there are a lot of international funding agencies, especially because Mahe is in India, government of India is doing a lot of funding. They have to look after for the calls and ask for funding and do aggressive research on AI. They form a group, and then that's how they can, that everyone can benefit by seeing practically what's going on. So according to my predictions, the current state of AI worldwide is in the early human baby stage. It has not crossed that stage even. Even the insects have much more intelligence than performing much more intelligent way than the advanced AI machines. So the AI, whatever we get confused or we get a hype, there is a hype for the terminology artificial intelligence. But the original aims of 1940s, 1950s, whatever the purpose they wanted to see, that was not being seen so far. That means machines were not able to think on their own beyond what was being told to them, even within the random framework. So the randomness also has to be well defined to the machines. For example, as we all know that during the Second World War, the ENIAC machines came up. And then during ENIAC machines, the random number generations were done that's how they initiated those days. The random environment was created by the computer. And so far, we could never call them random numbers. Although we use them, random numbers, they are pseudo-random. The reason we call them pseudo-random is, although humans, those are you generating computer-generated random numbers, they don't know what are those numbers, but computer knows it. Ideally, a random number means when you toss a coin, no one should be able to predict accurately the outcome of the coin tossing. But when computer generates a random number, be it a binomial model, Poisson model, any other model computer generates, computer itself knows it. Computer is not generating randomly. For you, it is a random, but computer knows the model which it is using based on the clicking time. So clicking time is a seed being given to the computer, and the computer generates. That's the reason they are called pseudo-random. So even that even the worst situation of randomness environment also, that is not purely random. Hence, we cannot go beyond that in the last 70 years. So whatever nearest, as I explained yesterday, I will again touch base very quickly on that exact deep learning machines. But before that, let me continue the talk, what was being missed in the introduction yesterday. So the productivity, the recent predictions by the job market and other shows that there is no clarity on the future AI-related job market. IT jobs are different than the AI. I'm not combining, there is a IT market, information technology jobs. But in specific for AI-related job worldwide, there is no clarity. And then there is no clarity even for what exactly the AI can do beyond health informatics. Health informatics, of course, the machines can do, because health informatics is it's about the finite number of combinations, like a chess. Playing a chess, a computer can be trained very well. You feel all the combinations, all the permutations of all the moves. That's the reason, if you all recollect, in the 80s, when late 80s, I was in the high school. There is a machine called Deep Blue. The Deep Blue machine beat that time the chess champion Garry Kasparov, because the Deep Blue machine, IBM Deep Blue machine, was fed by all the Garry Kasparov, the world champions, all the moves, and then it was a combination of them, permutations of them, computer being trained. But the same computer, same machine which was trained, which beat the then world champion, was beaten by third rank, fourth rank players at the same time, chess players. That means the computer which doesn't know other players' game, that could not generate on its own. So that is the greatest example that time. And then, jumping from there again, this is the chip, as I yesterday was mentioning. So one of the reason was computer training, machine learning, all these things was, if you do it in the language, if you do in certain language where letters have a unique sound, and those sound does not change with the context of the word, the context of the sentences, then the software industries are predicting that the machines can be trained more efficiently. So that's the reason, this chip is designed, you can see some Sanskrit language. It's not because I come from India, it's a Sanskrit language I'm using there. But the reason I use this is a demo chip I designed it, because Sanskrit language, the sounding of the letters always remain the same. So computer or machines do not get confused. Similarly, certain languages, like nature, N-A-T-U-R-E, but N-A-T-U-R-E, nature, the sound, computer U sound is giving nature, not nature. Similarly, C-U-T, we write cut. P-U-T, we don't write put, we say put. So computer have to be told each time, you pronounce like that, you pronounce like that in English. There are several modern languages, you see that the language has to be told to the machine. Whereas a lot of ancient languages, the sounding of the letters don't change with the context. So that kind of precision is needed for accurate AI. So the chip business also, the worldwide predicted that by 2025, these are all not my predictions. By 2025, there will be $91 billion market worldwide for the chip industry only, not AI industry. industry is different from AI industry because the chips can be used for AI, but what purpose these chips can be used, there is no clarity. But then there is a prediction that this increase of the chip production can be reached up to 91 billion by 2025. Just the market trend I'm showing. And leading areas of AI research, if you see language and speech processing, we see already there is a online you see that when you write a sentence, the computer automatically corrects it. So there is a lot of advancement already done in the AI, the language and speech processing. And there is also prediction that virus identification, as I demonstrated on the COVID, and virus research that I'm going to explain again. And also the toys, automatic machines, they are low tech. Low tech, as I mentioned, like chess game or any games, they are low tech because there are finite number of options. Finite number of options means all the options can be trained to the machine. They are called low tech. High tech means computer has to have some sort of intelligence on its own when the instructions are not given, or unsupervised training. Computer can computer bring a proper thought process into the needed outcome. Can it do that? All high tech implications of AI. So far there is no evidence that computer can do, like as we know that a lot of cars, driverless cars, have been halted. The trials have been halted because some one of the car already hit a pregnant lady crossing from a non-zebra crossing. So these kind of things are so far machines cannot be. There are a lot of such examples are there. And there is stock market trend, as I yesterday explained. Similarly, low tech industry AI can be utilized, and the AI system in practice, AI can be machine training, machine learning can be applied any situation in the world. But we are talking about the accurate or precise applications. Just by applying, like we know that Poisson model in statistics, we know a lot of normal distribution. We can apply normal distribution, estimate parameters for any data. But whether the data is suitable for normal distribution, estimation of parameter, model fitting, that's a different thing. Just because we have the computer programming, we can apply anywhere. That similarly, AI can be applied anywhere we want. But accurate applications or precise application, that's what only we are speaking. Only that is possible when the data and the association between the data, everything is mathematically well structured. So these are all the leading areas and the limitations of the AI. And the stock market predictions, the one can also, there are a lot of magazines are saying that AI can be utilized for predicting the stock. So before you buy a stock, you use the AI for predicting and then you buy. So that kind of things also one can see. Suppose you want to do that kind of thing, you can only have the data, you shortlist the variables, consult experts, consult the stockbrokers, various experts involved, and you will list out all the variables influence, and then you collect the data. But you can collect the data only up to certain time period, and you cannot collect the data for a future anyway. So you want to build a stochastic model for the future data which is not available, and then you predict the future value of a stock using it, so that the computer automatically the date you fix the date, the model based on the model you have stochastic model, computer can predict the value. But then can we build a mathematical model? No, because we know that association between the data points and the variables cannot be accurately defined 6 months before. So anything could happen. Any kind of crashes, this kind of COVID, the stochastic model you built in 2019 October, for next 6 months, in the March you saw what happened. So this kind of volatility models cannot be AI models cannot be incorporated beforehand, not even 1 week. You saw last week in the US, the 3 days back, there is a tornado hit certain places in the US, and you see that several industry manufacturing units all got demolished in no time. In 2-3 hours, everything got demolished. So this kind of unpredictable, this kind of things, AI models can never predict. So mathematically, we cannot have a well-defined model for stock market predictions anyway. So that's the limitations I explained. So the students students actually think of this kind of limitations, and why I'm explaining all these things are, they need to think beyond the hype. They need practically test the models on the ground, develop some prototype, experiment with it, and then demonstrate how best AI can be performed in the labs. And then mapping and microbes, as I was mentioning yesterday, there was a study in 2016 that actually predicted that publishing proceedings of National Academy of Sciences by two authors you see on the bottom of the screen. They say that globally there are about 1 trillion microbes are there, microorganisms are there. That many different species of microbes are there. So the question arises is, can we train the machines to predict the future microorganism? So COVID-19 is a microorganism. Could we have predicted in 2018 that 2019 we are going to have a COVID? Had we know all these 1 trillion microbes? No, because by the time you compute, another study says that I will show in the next. So before I jump into that, so far only 1% of the 1 trillion numbers are only identified. 99% of the microbes on the earth are so far not been identified in the labs. So once they have to be identified, then identified things have to be, as soon as we identify in the biological lab, we cannot train the machine. That information has to be digitized, and digitized information has to be translated into the machine. So far only 1% identified. Can you imagine that? How do we can predict? Even I heard, somewhere in Dr. Haslett is there. Maybe after the talk he can clarify. There are some companies in Australia or New Zealand. I heard they are charged. I saw in the news articles, they charge about $7 a month from if you subscribe their digital some subscription. They can predict. They can protect us from the some sort of the viruses. If we digitally they will see everything. They will take the data from us and they can protect from protection from the various things. I think I don't exactly remember, but they $7 a month. If you pay the digital health company, they protect us from something. That's what they advertise. So these kind of things, the marketing there, although they are doing practically, it is not possible to predict the future viruses. And then on top of that, these all numbers are 1 trillion number by these authors on the bottom. They also say that this is statistical estimate. No one exactly knows the 1 trillion number of microorganisms are there in the world. That's an estimate. Estimate itself means how much accurate that is. And then another study says that another article, it says that it takes thousands of years to discover the existing microorganisms. So whatever existing, if it takes thousands of years, how about the emerging microorganisms? So it's really challenging. So just because the computers are so advanced doesn't mean that we are going to benefit immediately from them. Suppose this is a study based on my own article with Dr. Stephen Kranz. We both published several articles on COVID. So one of the article what we demonstrated was, suppose these are the microbes worldwide. You identify them. These are the microbes available, and then we put the same microbes together, different microbes in a different way, a different color, or different. So these are all the microbes worldwide available. Suppose that theoretically are the microbes available worldwide. And once we identify them, you take them into the, this is all the globally, suppose identified. They are existing microbes. You are not identified existed microbes, and then you wanted to identify them. Suppose this is the 1 trillion of the samples, 1 trillion of the microbes, and then you want to identify them. Once you identify them in the lab, you want to digitize them. So some of them you see that the square with digitized numbers. That means these microbes are identified and digitized. And some of where you see that only white squares. That means they are only identified, not even digitized. So there is a distinction between the identification in the lab, in the biological lab, is different than the identification and digitization. So digitization means everything has to be in a binary code. Computer need to understand, the machine need to understand. So as soon as that means you scan a photo and save in the computer, doesn't mean that computer understands that's a microbe. So there is a lot of difference between digitized photo in a computer in a machine is different than digitization of the microbe. Suppose some of them are digitized, some of them are non-digitized. So that means we cannot predict, even we digitize partially, we cannot predict the future microbes. And as I'm quickly moving to the another this thing, future area of AI research, virus research. Suppose you're using RT-PCR or PCR, you create the parameters, and then these parameters can be some various thousands of experiments worldwide you can do, and this is you each experiment you collect, you make a parameter space, and then thousands of experiments you create a super parameter space. That super parameter space one can use into the machine, and machine can predict future virus from the combination of the permutation of the both permutation combination of the parameter space. The machines can be trained to make a permutation combination of these parameters and create a new viruses. And then this is my idea. That's what we are asking now for the $5 million grant to really practically do it. This is the end game for the AI. If you successfully do this game, do this experiment, and then perform it, whether AI can predict or not will be clarified. How far AI, how extent AI can be clarified. The other day when I was giving a talk on that, someone asked, can we predict 2022 COVID if there exists such thing? Yes, we can predict, but there is no guarantee that will occur unless the 2022 finishes. That means AI can be used to predict, but we cannot guarantee that can occur for sure. That's the current state of AI. So we want to continue that. Then parallelly in the lab, once you finish up the experiment in the computer, machine is being trained, and the figure Z here, that means this part of the figure shows that the machine developed viruses compared with the laboratory developed viruses to match how accurately AI can predict. So these sort of experiments are very expensive, and this needs a lot of experimental time and also the machine training time. So we are predicting that it takes 3 years, 3 years at least, to finish up this kind of experiments, and then only we'll know. And then as I mentioned, this is the first time AI being promoted to test that the COVID identification, and how this model works. In the first phase, the travel information being collected, and later, as I mentioned, this inspired for various other apps all over the world, including the Arigya Setu. And the back end, the front end, the information is being entered by the front end through using the mobile phone. Any individual can enter 18 plus, and then the back end. Once the data entered and sent to the hospital, I mean the back end, the hospital, the machines evaluate whether that person who responded in the mobile phone needs a further testing, or a mobile van can be sent to home if it is in a quarantine. So the individual also receives a barcode. As soon as that individual receives a barcode, same time the nearest testing center also will receive a barcode, so that these two can be matched. So there is no misuse of the one person entering the mobile data, another person going for testing can be avoided. So, and then using GPS information, everything will be included in the model. So the geographical regions are there, and as I explained yesterday, this will be the yellow dots are non-responders, and the circles are responders within a household, and the non-responders can never be we can never know their status. So some of the non-responders also could be positive, but we will never know, and no AI model can predict that. So that's the idea of this the first AI identification model. And yesterday I did not show this slide, but recently me and my collaborator is a well-known statistician, Professor Anil Gore. He and me were developing together a model for judicial systems in India. How far we can apply artificial intelligence for decision making in the courts, because as we know that a lot of thousands of cases have been piled up in the courts. Can we make a decision, at least for the small kind of things like a bail, giving a bail? That itself is a big achievement. If courts can take a decision for granting a bail, a lot of pending cases are there. So we initiated and we developed a function. So the question is, I think roughly, I don't remember, I recollect that there are about 17,000 cases are filed every day. in Indian codes for smaller things, So can the AI can be used to shortlist those cases and decide instantly whether bail can be granted for them. So can we use AI? That's the question we asked, and we developed a function. I'm not going into detail. So he has been working a lot, and then he's well-known applied statistician in the country, and he worked also as a chief. He worked as a National Statistics Commission. So we are almost close to get this article. So we developed an interactive function. That function takes a decision. They helps the judges to take a decision, and then final judgment will be given to the judges. Finally, it's not that machine automatically declares a judgment, but then the judges will consult because it's on the trial phase. So we suggested to have a pilot study, so that we'll all know. Yesterday I could not include this slide. So today we discussed, me and Professor Gore, and then we thought to include this slide in the. I took his permission we both decided, this is a good opportunity to share the ideas. So this will be the more details will be maybe some other time. I'll describe the complete algorithm used in this AI algorithm used for decision making in the judicial courts. So again, coming in summary, incorporating actual intelligence to the machines are impossible, or machine is impossible. So the next best alternative is exact deep learning machines. So I will again quickly, the technicalities of that I would like to explain. Suppose an object is described with a finite number of distinct attributes. Attributes means here that how far we can describe, that I called here attributes. And these attributes, suppose, do not change over time. This is a simplistic case. Under that situation, that means suppose an object can be described using a finite number of distinct attributes, and these attributes are not dynamic. Under that condition, the machines can be trained with a probability 1 to detect this object, wherever that object may be in the universe. And this is exact. Why? So deep learning neural network, all that, some of the most of the audience I have some idea about that, but neural networks, there is a lot of uncertainty because the randomness is involved there, and due to randomness, uncertainty is piled up or uncertainty is reduced, but we never know which way it is happening. But exact deep learning, the idea is that there is no uncertainty. We'll see how. So it's a central idea. And then the idea is, I will explain that. Suppose the object, whatever I mentioned, I called it O, and uniquely explained by, say, Y1, Y2, Ya. Some notation I gave. A number of attributes are there, and these kind of attributes can be treated as a description, how far you can explain that object. Any object. If it is a bulb, how various ways of explaining. If it is some rock, we know how various ways of explaining, but it should be finite and finite number of ways, and that should be unique. That should not change over time. If you call certain thing some sort of rock A, that should remain rock A. Some other new quality should not be added to rock A forever. And then these attributes choose exactly pre-decided values, because all kind of such rocks you collect, and then you decide the values or some ranges, some dimension, whatever way you want to describe that these attributes have some values. So you decide whether certain values are present or absent. Let there be so many large number, 1 million numbers are there to decide. Still fine. Machines can be absorbed with that kind of large number. That's not a problem with the machines. Machines can be used to insert as many large numbers as possible. That's not a problem. So Y1, Y2, I code them as various ways. Ya, and then I call the vector YC. Suppose the machine is fed with a triplet of information: object, attributes, and then these Y values, pre-decided values of the attributes: object, attributes, values of the attributes. So triplet, and then these number of all possible permutations that could determine the object O is nothing but the product of the C1, C2, CA. C1, C2 are there. These need not be, I wrote it like that. That doesn't mean that C1, C2, CA are equal number. C1 could be equal or unequal to C2, C2 could be equal or unequal to C3, and so on. I just wrote it like that. So, yeah. So now, in the universe, omega be set of all objects that can be classified as O. Then, the cardinality of omega would be less than or equal to the product or greater than the product. There is no third option. I mean, already three options are there, less than or equal to or greater than, no other fourth option. So we pick an object. Any object we pick. Machine already have the information, say 1 million of combinations are there, the triplet information is there, however large, be it a finite, keep maintain as long as finiteness is maintained, you put into that. So given object, machine can detect whether the object you show to the machine, whether that is part of omega or not, at least that machine can say accurately. Like, there are experiments are done. For example, I forgot to quote that. A machine was given a figure of, the 1 million different kinds of cats images have been trained to the machine. I forgot the source. Not by me, definitely. That kind of experiments when images are being trained to the machine. 1 million plus 1th image of a dog which look like a cat is checked with the machine whether it is a cat or dog. Machine decided it is a cat because machine doesn't have its own intelligence unless the information is properly given, and this 1 millionth image was not part of the 1 million images of a cat. So a new image which doesn't belong to the 1 million images, which is a dog look like a cat being asked to the machine said it's a cat. Imagine that many combinations of images are, even though that much information is having a machine, that machine cannot predict something unknown. But a 3-month-old baby may not express what is a cat and what is a dog, but the baby can distinguish. 1 million cats the baby would never see, but by looking at, by playing in the ground somewhere or looking at home, the baby never gets confused because baby has its own intelligence. The baby knows by looking at 10 cats, hardly maybe 11th he sees a puppy look like a cat, baby never gets confused. Baby thinks, although baby may not express. So this kind of information, the exactness, there is a lot of this is the best possible way. Realistic AI is still not possible. Because robots, as I explained yesterday, the cleaning robots are there. One can use the robots for cleaning the home and cleaning the carpets. And then as soon as you put a dust, the robot automatically go there and then clean it. So that's a finite, that you define the range, GPS, everything, and then certain granule size, robots can go. That's a low tech. That doesn't need some unknown thing. And that kind of cleaning robots also, when the granular quantity is bigger than certain quantity, the size of the granules, robots cannot clean. Because that information has to be told to the robots, cleaning robots. So the object detection is done for sure if the attributes are matched and there is no uncertainty here. Although the utility may be only for finite situations, but then there is no uncertainty. That itself is a big advantage. So as I mentioned, I don't want to again show the same, almost a lot of 300 to 300 beyond 300 medias worldwide in various languages. They reviewed my work on the COVID because that was the first that time, and you can see Google, not a problem. So as I mentioned yesterday, I'm launching a new journal during the 75th year of India's independence with world-class editors, as I have a lot of experience of editing the various journals, world-class journals. In fact, I'm editing now a special issue for Journal of Indian Institute of Science, the theme probability and statistics. Another for the Elsevier, I'm reading Journal of Mathematical Analysis and Applications by Elsevier on the COVID mathematical analysis. And other various other handbook of statistics I have been editing with Professor C.R. Rao for it's a great opportunity and learn various things on. During the 75th year of India's independence, I want to launch with the help of top class world class editors across the world in various countries. So that will be there. Ganita Prabha, the title of the journal. It is not there, groundwork only going on, and when it launches, you all will know. Thanks a lot for all your attention.
Thank you, Professor Arni, for a fabulous overview of various applications in presence of uncertainty as well as when there's no uncertainty. Any questions from the audience?
Thank you, Professor Kamath.
I just have one clarification. One of the concerns always when we deal with this kind of model building is overtraining. So are there any mechanisms that you can use to check on this as we train the machines?
That's a good question. Overtraining is also an important aspect, but it doesn't harm. It's a waste of time, but it doesn't. Machines won't be affected. It's a repeated information. Overtraining means you tell same things repeated way. So machine can be made to check itself. If they repeat it, don't take it. Machines won't take it. That's not a problem. But it's a way, only time consumption wise, that's a waste of time for the machine. But it's an important aspect. You are right. I agree with you. It can be optimized. Machine training can be optimized. That won't gain the performance of the machine. Overtraining won't gain its performance.
Okay. Raksha, any questions from the hall there?
No, sir. No, sir. No, madam.
Okay. Thank you, Professor Arni, for your talk and giving an insight into various applications of these exact deep learning and artificial intelligence. I am sure that the budding statisticians, mathematicians, and data scientists would have really, gained knowledge as to how to begin with applications of these for their future learning curves. Thank you, Professor Arni.
Yes, especially Mahe, as I explained in the beginning, Mahe, since it's a private institution, so they are more free. They don't have to be bounded by some regulations by UGC or CSIR or any MHRD. Of course, they have to follow certain regulations of the training part, but research-wise, as long as the institute regulation, review boards are satisfied, they can take up a new projects and innovative, creative works of combining formulating a big teams, and then bring newer experimental results, and then publication. Publication, of course, is authentication is needed. So yeah, in that sense, in fact, from yesterday to today, the changeover is for me advantage of. Professor Haslett wrote a very detailed email, and he appreciated these things. So I took more. It's like a tonic for me. So I took a more energetic way to, more aggressive way to, and then Professor Prasad also nicely commented. That helped me to, these things I could not as yesterday add about the Mahe's role and also AI in judiciary. So you all will see that the practical implications of in the judiciary also. The 17,000 cases per day are being filed. How far we can reduce the times in the courts of law? You also see in the news where certain Chief Justice of India also mentioned that this is going too slow. So whether AI can be applied, so realistic way, like Mahe can think of those things. Once again, I want to thank all.
Yeah, thank you for your
suggestions. Next time when you visit India.
Yeah,
sir.
we look forward to having some collaborative work with you, definitely.
Definitely.
So we'll see when things ease how we can have you with, visit Mahe.
Absolutely. Love to see you all. And I will attend Professor Hazlitt talk, then I'll quit myself. Okay.
Okay, so for the next speaker of this session is going to be talking about the building blocks, concepts related to the building blocks of predictive modeling. All of us know that linear models is one of the building blocks in predictive modeling. So we have with us Steve Hazlitt from Massey University, New Zealand, who would be talking on role of block diagonal matrices in conditions for equality of best linear unbiased estimators in linear models. Over to you, Professor Steve Hazlitt.
Thank you. Now, my talk has actually been recorded, so I think we'll listen to the record, and if you want to ask questions at the end, that'll be fine. So thank you very much for the introduction. To talk about today is how block diagonal matrices matter when you're looking at conditions for equality of the best linear unbiased estimators and linear models, particularly when you've got two models. So if we look at the abstract that I wrote for the conference, what we're going to do essentially is to look at conditions when the best linear unbiased estimates are unaltered, when there's a change in covariance structure. And what we're going to look at is to extend this into the situation where we have one full model and one small model, which is a nested model within it. And later we're going to look at the intermediate models as well. And what we're looking at is under what conditions do the best linear unbiased estimators remain the same? What covariance structures are permissible if we must meet requirements for all of those models rather than just one of them? So we've got other papers which have looked at best linear unbiased estimation. I'm not going to talk about those in detail very much today. So the key question we're addressing is what variations in an error covariance matrix are permissible when two nested fixed effect linear models must both retain the blues for estimable functions of the parameters that they share. And then we're also going to consider models that are intermediate between the two, which happens when there's more than one difference of one parameter between the full model and the small model. I'm going to start this with an example. Here's a couple of possible Y vectors and design matrices X. And when you look at those, there's Y and Y new, there's X and X new. And on the surface of it, there doesn't seem to be very much connection between these at all. If we find the best linear unbiased estimator for the original data, what we get is this. We get beta hat in the first of 2.4 minus 3.8 for the Y and the X. But if we use Y new and X new, we get exactly the same set of best linear unbiased estimates.
We all know.
With exactly the same covariances for these as for the original data set. So what I'm going to address and answer toward the end of this talk is why and how, but we're going to have a few sections to work through before we get to that point. So we're going to look at two nested linear models, a full model, which I'll denote M12, and a small model, which I'll denote M1 using script. And here's the first one, is numbered 1, and number 2 is the small model. So the first one is the full model, and the second one is the small model. And you'll note that what we've lost is the x2 beta 02. Now I've used 02 as the subscript for reasons that will become apparent shortly, but both of them are set up to have the same covariance structure. We've got to get through a little bit of notation. We're going to let y be the response variable, e the errand mirror, variance v0, which is the original variance, expectation 0, and we've allowed x1 and x2. Sorry, there's a slight problem there. This is meant to say r for the real line, and similarly we've got x is n by p, and it may be partitioned, and similarly beta may be partitioned. We've got various things for generalized inverse, more Penrose inverse, column space for A and for its orthogonal complement. We've got a projection operator denoted PA. We've also got the situation where we're interested in the difference between that and the identity matrix. And when A is equal to X, we're going to use M for the IN minus PX. For I and MI with a subscript for I equal to 1 and 2. And the obvious choice for the space that's, or the matrix that's perpendicular to X is M, this choice of M, IN minus PX. Now the core result from Rao, which is this 1971 paper, theorems 5.2 and 5.3, the necessary and sufficient condition, we're only dealing with one model at the moment, put aside the full and the small one for a moment, is given by this equation here, for the model to have the same best linear unbiased estimate for x beta. So it's V equals the original V0 plus x A x transpose plus V0 x perp B x perp transpose V0. And I'd like just to note that x and V0 x perp are orthogonal with respect to the original covariance matrix, and that A and B are arbitrary, conformable, and hence square matrices. They're not of the same dimension, but they are both square. So we've got additional terms that we can add to V0. And the curious thing is that this is not necessarily a full specification for possible V, but it is the specification for V if we were going to meet this condition for the blues. Just a piece of occasional pieces of housekeeping. The first one is both the matrices A and B are square, but they may not necessarily be symmetric. Rao's original formulation set them as being symmetric, but it's not necessary, because if CEC transpose is itself symmetric, and then if you take transposers, we get the equation CEC transpose equals CE transpose C transpose. And if we play around with this just a little, we can construct a form from E and E transpose by adding them and dividing by 2, which is symmetric. So regardless, we get the same result, whether it's symmetric or not. If it's not symmetric, we can create a symmetric matrix which has the same property in terms of the quadratic form. Now, if A and B are symmetric, we're going to set A equal to U transpose and B equal to UR transpose. And I've chosen R because it's linked to residuals, but we won't go into that in detail at this point. So this equation now looks like this. B equals V naught, and we've got the term in quadratic form in X and the quadratic form in V0 X perp. And the two can add to V naught, and that provides a V which covers all possibilities. All right, so we're going to go back now to full model and small model, and I'm going to work a small trick. I'm going to reparameterize the full model and call it, instead of M12, I'm going to call it M12T. And the thing I've done is I've pre-multiplied X2 by a projection operator, which I've called PX2 given 1. And then I've renamed PX2 given 1x2, I've renamed it X2 given 1. Now, the reason I've done this is because I want to structure this problem so that it's equivalent to fitting beta 1 before I fit beta 2. And if I use this transformed variety, then there's nothing in fitting beta 2 that's going to have any effect on beta 1, because beta 1 essentially has been fitted first. So we've got a couple of projection operators in here, one onto the column space of x1 and one onto the column space of m1 x2. So these are invariant, both of them, because the choice of generalized inverse doesn't matter. And the reason I'm doing this is because, as I said, I want the column spaces of x2 given 1 and x1 to be 0, to be the null set, so that they're orthogonal to one another. So, as I said, the implication is that we're essentially fitting, it's the same as the original model, except we're forcing that x1, beta 1 be fitted first. Now, having done this, we want to make sure we can get back to where we started. And equations 8 and 9 provide an interconversion between the two. And the reason for this is that if we get, in the end, we get x2 given 1 beta 2, we want to know what that is in terms of x2 beta 2 0, which was the original structure where x2 may have column space that overlaps with the column space of x1. So this provides a conversion between the two. So the important point is not to remember this. The important point is that even with this transformation, we can get back to the original model and start to look at conditions where we got x1 and x2 rather than x1 and x2 given 1. Now, if we rewrite equation 5, in terms of x1 and x2 given 1, we get this. And the thing I'd like you to notice is it's got a structure with V naught as usual. It's got a quadratic form in x1. It's got another one in x2 given 1, and it's got one in V0 x1 2 perp, which is the space perpendicular to x, or x1 2 combined. But it also has these additional terms which contain like x1 u1 u2 given 1 transpose x2 1 transpose, and the transpose of that whole term. So what we find is that there are additional terms in here that we're going to have to try and deal with. But that's for the full model on its own. And for M1, we've got a parallel result that looks like this. And it's got x1, and it's got the other part involves the column space of V naught x1 perp, which is the column space perpendicular to only x1. So I've got just a little bit of notation here because I'm going to use this in some diagrams that are going to help explain what I'm talking about. So I'm going to use V naught x perp to mean V naught x1 2 perp, and V naught x1 perp to mean V0 x1 perp in terms of the notation that's written there. And if we've got a part of a a product involved of a quadratic form or something similar. We're trying to represent that the relevant part of the entire U matrix, which is made up of U1 and U2 and U1, 2R. If we're trying to do that, I'm going to represent that simply by setting the relevant part of what I've called U0 transpose to 0. So a diagram. So what we've got is these are the necessary conditions in terms of this internal matrix, but I really want you to read this as the product of what's in the first column times what's in the matrix times what's in the column headings. So although I've represented it in terms of the U matrices, it's really the product that is 0, not the actual U terms. But we can represent this quite nicely because if we look at the first one, which is the full model,
Good afternoon.
the one on the left, you'll see that the areas in yellow must be 0 to meet Rao's conditions. And for M1, the parts that must be 0 are represented again in yellow, but they're different. But you can sort of see where this is going, perhaps. Because the core question is, what can we do to make sure that the conditions on V work for both of these models? And you can start to see that we might want to be setting some additional parts to 0 in both of them of that internal matrix in order to make sure that the diagrams match up. Well, that's the heuristic. The
information required about the technology which I have talked just now.
Clear
you can just send me an email. Also, I would like to say that the images presented in this presentation and the slides, they are being taken from the various resources from the web. I don't have any claim over them.
In order to get blues to be unchanged.
Thank you very much.
Thanks
a lot.
Now, this is sort of something particular. And again, I must apologize because there's a little square box in the fourth line here, which is really meant to be an indicator that that's the real line. So that's RN. Something seems to have gone slightly wrong with my copying into PowerPoint. So the point here, though, is that these are the reason this doesn't work very well is the column spaces don't actually align of CX, so the column space of X1 and the one for V0 X1 perp, and the other ones which apply for the full model. So essentially, using the representational colouring that we had, and I'm going to use this for a set of figures, what is required in figure 1 is that all submatrices of the entire matrix that need to be 0 in either model need to be 0 in both models. Now, I'm going to do something here. The collection of column spaces for V0 X1 perp and column space for X1 actually is RN, and so is that true for the full model. There's a different set of column spaces. So what we're going to do is we're going to look at V0 X1 perp, and I'm going to divide it into two parts. One part relating to the column space of X2 given 1, and the other related to the column space of V0 X1 2 perp. And you can sort of see why I'm going to do this when you look back to the diagram. Now I can do this because in the model, the small model M1, the column space of X2 given 1 is now within the column space of V0 X1 perp, and I just want to divide it up into two parts. And the reason I want to divide it up into the two parts may be clear when you think back to the diagram. Now, I want to look at a restricted form of equation 10, and you'll notice that I've dropped out the terms that begin X1 and finish with X2 given 1 perp and its transpose. So I've dropped those out, and I've structured something here, which I'll provide a diagram for shortly. So the terms in U1, U1, 2 are transpose, and U2 given 1, U1, 2R transpose, and the transposes of all of those must be 0 in equation 12, because if we apply the condition that Rao uses to prove his theorem, those terms don't get set to 0 in themselves. But what we're going to do is now set them to 0 by construction. And for M1, we've got a similar thing. This equation 13 we've seen before, but we're going to have to provide some restrictions to it. Only this time, the restrictions are going to be within the column space of V0, X1 perp. And so the restriction is that we're going to split that term so that it's made up of two components without cross product terms between X2 given 1, or not cross products, sorry, X2 times U2 given 1 times U12 transpose X12 perp transpose V0. All right, so that leads to this equation here, which fortunately is exactly equation 12, which is the one that applied for M1 to T. So the structure that we're going to look at is necessary and sufficient because no other structure can ensure that the conditions required for M1 to T and M1 to retain their best linear unbiased estimates simultaneously are going to be met. So here's the picture. Now, a couple of comments about this. I'd like to look at where the dashed lines fall. The dashed lines on the left fall that divide the diagram into equally sized squares. And the main part, where with the two off-diagonal areas blocks being yellow, that has lines that correspond to the ones we've seen before for M1 to T. And the dashed lines for M1 correspond to the ones we've seen before as well. But what's important here is the only things that are allowed to be non-zero are the diagonal blocks in both cases, despite the fact that one of them has a slightly different color to the one in the other diagram. So there are 3 diagonal blocks. You're allowed to have non-zero elements there, but both the yellow and the orange parts have to be 0. Okay, yellow and orange parts are 0. The rest can have something that's not 0. But we structured it so that we can subdivide the space of the term that begins V0 X1 perp. We can divide that, and we can also divide the part that corresponds to the original X matrix, which is made up of X1 and X2 in the full model. So the division that we're doing in the full model is different apparently to the one that we're doing in the small model, but what we're left with in both cases is it's the diagonal blocks that can be non-zero. And that's the diagonal blocks is essentially what we specified in the previous equation. We were dropping out certain terms, forcing them to be 0 or setting them to be 0, or they're 0 simply because of the result of Rao's theorem. Now, the reason I'm using M12T rather than the original form M12, because M12, the original thing, because X1 and X2 may share parts of their column space, it doesn't provide any straightforward way to specify the condition for V that M1 to T and M1 coincide, or M1 and M12 and M1 coincide, the full model and the small model. So that's why we're working with this transformed version. Now, there's more detail as to why this is the case, but I'm not going to hang on that. Basically, because it's to do with setting up these column spaces carefully so that they partition in the same, can be partitioned in the same way. One part of that is to look at X2 given 1, and the other part is to look at partitioning the column space associated with V0 X1, the small model perp. All right, so we've dealt with that. The next question is what to do with intermediate models. Now, this happens if there's more than one extra parameter in M12 or M12T compared with M1. So we first consider the case where X21 is a vector, and which makes beta2 a scalar. So there's only one additional parameter and one additional column for X2 given 1. Transpose. What we end up with is this diagram, and again what we've got is we need the things down the diagonal to be, we're allowing them to be non-zero, the blocks down the diagonal, but all the rest has to be 0. So the orange and yellow parts are 0. But what's important now is if we look at the left-hand diagram, x2 given 1 is a vector. So that light blue area is a scalar, simply one value. So what's going to happen shortly is we're going to look at what happens when we add yet another parameter. In other words, there are 2 parameters in between. But again, the same structure that we've seen before with only the blocks down the diagonal being allowed to be non-zero will apply. Going back to this case where x21 is a vector, what we get is this result. And the term in the middle there contains a scalar, u2 given 1 squared. So it's represented in the diagram by the scalar that was in light blue. And if we extend it to another parameter, then we're essentially repeating this process, but we're only allowed to add diagonal elements to u2 given 1, u2 given 1 transpose. So we get a very similar diagram, but now x2 given 1 is a matrix, not a vector. But the point and crucial point is that we've got blocks down the diagonal, which can be non-zero. Everything else must be 0. But the light blue area must be diagonal. So we can continue this process. Won't matter how many parameters we have in between, the full and the small model. Down the diagonal, we're going to, of the blue component in this diagram, are going to have to be, or can be elements that are non-zero, but off the diagonal of that block matrix, they're going to have to be 0. So there's internal structure in the light blue matrix that isn't always the case. In other words, this diagonal requirement is the one that actually applies when you need the intermediate models to have the same best linear unbiased estimates as well as the full and the small model. So I've represented that here by using diag on the matrix u2 given 1, u2 given 1 transpose. So the central term in here corresponds to the light blue in the diagram. Now, we've done this in terms of u2 given 1 and x2 given 1. If we go back to the original model, we can transform this back into a result that applies for x1 and x2. And what happens then is, when you look at the diagram, there are terms that can be cross products between x2 and x1, or involve x2 times f times x1 transpose for some non-zero f. But those f's are the f's that are possible, and it's not a general f, it's actually tightly specified by the requirements that come through by looking at the situation where we've got m12t, the transformed version. This can be extended, and we can extend it to the results of section 1 to 4 can in principle be extended to mixed models. And the way we do that, or the way it can be done, is to one method involves using x equal to, with this structure, and v equal to this one. We're assuming for the moment v naught equal to this one. We're assuming for the moment that v, 0u, and r are uncorrelated. And we note that x perp in this case is made up of this matrix that are given here. So essentially, we can substitute these in, and the formula that we've been working on previously should apply. I'm going to look at the intermediate models between a small mixed model and a full one. The parameters we may be adding or taking out, depending whether we start with the full model or the small one, are either fixed or random, or they're possibly both. And as a preliminary, if we want to think about it, the reason that the sort of motivation that would help in understanding what would happen is we consider this addition or the taking out of parameters, consider them one parameter at a time, as we did in the first part of section 4. And that helps keep track of which ones are random and which ones are fixed. We may want to delete 3 or 4, but we only need 3 or 4 parameters, but we can think about it in terms of deleting them one at a time, whether they're fixed or random. To conclusions, I just want to go back to the example. The fitters via ordinary least squares that produce that data. So V naught is sigma squared I. And in the example, I want to look at, to allow models to be reduced to the simplest form, only an intercept, which is the final parameter estimate that I provided in the example at the beginning. I'm only going to add to this term in V0 x12 perp. It's the only one I'm going to add. And I'm going to make life becomes relatively simple because V naught is sigma squared I. So we get sigma to the fourth and we get this x12 perp U12R multiplied by its transpose. Now, this is produces, using this and adding it to V naught, produces a new V, new variance covariance matrix. And I can find the inverse of its Cholesky or Eigen decomposition, V to the minus a half. So if I do that, and we can use different selections of U12R, anything you like, and pre-multiplying the original model by V to the minus a half, having done that, I can produce an infinite collection of data sets that will have the regression coefficient, same regression coefficients as the original data. So diagrammatic, what we're saying here is we're only going to, this isn't a necessary and sufficient structure, it's a sufficient one. So what we're going to do is we're going to forget all the other block diagonal terms that could be non-zero and set them all to zero, except for the green area, which is associated with the column space for V naught x12 perp. Diagrams are structured the same way in every case, so the structure in here shouldn't be too much of a surprise. But what this does also allow us to do is if you just look down the first column on the left-hand diagram, you'll see that it isn't x2 given 1, it's just x2. So by setting the whole of that to 0, I don't have to worry anymore about whether x2 is perpendicular to the column space of x2 is perpendicular to the column space of x1. I'm simply going to set all of that to 0. So the same set of additions to V naught will work for all submodels because of the way we've chosen the term that we've added. There are no terms in x2 given 1, U21, and it's multiplied by its transpose, so we don't need to orthogonalize to form x2 given 1, as I just said earlier. Now, in the example, it's pretty straightforward because you may not have noticed, but in fact, the first model, the original model, is a polynomial model, and they could have used orthogonal polynomials. In general, though, this orthogonalization is an extra step. And the other reason for adding this is it focuses on changes to the original covariance matrix that belong in the column space as the residuals to the full model. And they belong in the residual space for the full model, the column space for that, and hence they apply, they will work for all the fitted models that are subsets of them or small models. So what we have now is a way of generating new data sets from the original data set, and the new data sets will have exactly the same best linear unbiased estimates, not just for a complete model that you may wish to fit, but for every submodel you can create from it. Now, the idea has been used before, and we've tried using it for data cloning. The usual arrangement is to repeat the data many, many times. And the repetition of this data is often used in Markov chain Monte Carlo models. What we're offering is an alternative. We can also use it for data visualization, for seeing what these other regressions would fit, what their residuals look like. We can use it for smoothing. We've used it for, using it for confidentiality and encryption, which are basically, that unless you know what has been added to V, you can't work out the original data. But this can be used by government statistical agencies, for example, to provide data sets for which every regression that you would wish to fit for a given set of variables or their interactions, if you wish to include those. Every set will give exactly the same results as the original data, but you don't have the original data, but you do have unit record data. And for encryption, what's required is not to know what the U matrices are that you've been adding. So some of the methods are outlined in a paper I wrote with Raj Raju back in 2012. Thank you very much.
Thank you, Professor Haslett, for this insight into the elaborate mathematical background in the role of block diagonal elements. Any questions from anybody in the virtual audience? Raksha, anybody in the hall? Professor Haslett, correct me if I'm wrong. To me, it looked similar to the variance partitioning that we do in the mixed modeling, the approach that is seen here.
I'm not quite sure what your question is, but the fact is that when you start looking at mixed models, you do partition the variance, but it doesn't necessarily guarantee that your estimates remain the same, whether they're estimates of variance or the parameter estimates or the parameter predictions in the case of the random effects, whereas this is looking at a very particular type of structure, or apparently very particular, which will give you the same estimates and predictions for random effects. I suppose that, one of the interesting areas that follows off, of course, is that even when you don't have that condition, you often want to know that changing your model is not going to affect your parameter estimates very much, and this provides some guidance on that, an indication of how close you might be to that situation. So I think although what I've been talking about is mostly linear algebra, I think that there are a wide range of applications. As I've said, confidentiality and encryption are certainly two of them.
And in some practical scenarios, there could be a possibility of near singularity of some of these block diagonal elements. So what would be the effect of that?
Well, the original variance-covariance matrix in this structure need not be full rank. Okay. Could be singular. What you're adding on could, of course, be singular, but you do start with a V naught, and it changes that structure remains. But there's no restrictions on what I've been talking about in terms of needing matrices to be positive definite rather than positive semi-definite. We could. It applies to a V that may be singular and consequently needs to have a generalized inverse rather than a morphic rather than a full inverse.
Okay, I think there are no more questions. So thank you very much, Professor Stephen Haslett, for this insight into the deep mathematical techniques in the role of block diagonal matrices for best linear unbiased estimators in the linear model. Thank you very much. Have a good evening.
Thank you.
Raksha, over to you. Jai.
Thanks a lot, Professor. Thanks a lot, Professor Haslett and Professor Arni for joining us. And thank you, Asha ma'am, for chairing the session. Let us have a small break now. We will join after 11 o'clock. Next session is a contributory session. See you soon.
ಟೈಮ್ ಉಂಟಲ್ಲ
But huh? Now I'm audible, right? Okay.
Welcome back, everyone. Now we have a contributory session, and this session will be chaired by Professor Srimati Maya from Prasanna School of Public Health, Manipal Academy of Higher Education, Manipal. Speakers of this session are as follows: Pooja BS, Department of Data Science, Mahe Manipal. Title of her talk is Multi-Level Analysis of Self-Reported Asthma Prevalence and its Risk Factors in India using NFHS4. Another speaker is Raksha Pujari from Mahe Manipal. Title of her talk is Two-Stress Regular Graphs. And the third speaker is Uma Shankar Kelattaya from Mahe Manipal. He'll be talking on a note on reverse order law for outer inverses. I now request Professor Srimati Maya to take over. Over to you, ma'am.
Okay, welcome Pooja. I request you to present the topic, that is a multi-level analysis of self-reported asthma prevalence and its risk factors in India using NFHS data. Yeah, you can start now.
Good morning, everyone. I am Pooja, a research scholar in the Department of Data Science, PSPH Mahe Manipal. Firstly, I would like to express my gratitude for CARMS for organizing this event and giving me this opportunity to present my paper. The title of the work is Multi-Level Analysis of Self-Reported Asthma Prevalence and its Risk Factors in Women in India. So, the flow of the presentation is as follows. We'll start with the introduction to the topic, then objective of the study, then we'll specify material and methods used in the study, then results obtained, then we'll conclude the presentation. So now, coming to the introduction to the topic. As most of you know, asthma is a common and potentially a serious non-communicable disease affecting both children and adults. What happens when we have asthma is the air passages in the lungs become narrow due to inflammations and tightening of the muscles around the small airways. So this will cause the asthma symptoms such as coughing, wheezing, shortness of breath, and chest tightening. If you look at the statistics related to asthma, among the total Indian population, about 6% of children and 2% of adults are suffering from asthma. If you look at the global level statistics of asthma, globally, asthma affected approximately 262 million people in 2019 and caused 461,000 deaths. Among these 461,000 asthma-related deaths, most of them, means more than 80% of them, occur in low and lower middle income countries, example India, where underdiagnosis and undertreatment is a challenge. And if we look into epidemiological data, they are indicating the bias in the asthma prevalence and severity. And this asthma instance, prevalence, severity, and mortality seem to be higher in women compared to men overall. So looking at these evidences from the previous studies, we have taken up this study with the aim of understanding the socio-economic and behavioral risk factors associated with asthma among women in India. So now, coming to material and methods used in the study, we used the data from National Family Health Survey 4 of India that was conducted in 640 districts of India in 2015-16. This survey collected the information from a nationally representative sample of 601,509 households, in which the total of 699,686 women aged between 15 and 49 were interviewed. And this information obtained from women has been analyzed in our study. So now, when it comes to nature of the outcome variable and explanatory variable, in the survey, the prevalence of asthma was ascertained based on a single question. That is whether they have asthma. The answer was yes or no. So the outcome variable was binary in nature. Coming to the explanatory variable considered in the study, they were all categorical in nature, and some explanatory variables considered in the study are age of the women, education of women, type of residence, wealth index, availability of improved source of drinking water, improved source of toilet facility, clean fuel for cooking food, a separate room used as a kitchen, household with no crowding, consumption of tobacco in any form. So coming to the statistical methods used in the study, first we used chi-square test to check the association between outcome variable and explanatory variable. Then we used multi-level logistic regression to find risk factors associated with asthma. So now the results. This is the table giving prevalence and odds ratio, that OR is odds ratio of asthma among the women aged 15 to 49 years by household environment and background statistics, characteristics, India 2015 and 16. So the results indicated that 1.6% of the women aged 15 to 49 in India were suffering from asthma. It was evident that the prevalence of asthma was more among the women of age between 44 to 49, and they were 3.6 times more likely to have asthma compared to teenagers. Then the prevalence of asthma was negatively, it was evident that the prevalence of asthma was negatively correlated with the education. That is, higher the level of education of a woman, lower was the self-reported prevalence of asthma. Supporting to this statement, the odds ratio also showed that women with primary or no education are at more risk of asthma than the women with higher education. Then the asthma prevalence was found to be higher among women who did not use clean fuel for cooking, that is 1.53%, compared to other group, that is 1.37% in another group. And the odds ratio also showed that women using clean cooking fuel are comparatively less likely to have asthma. It was clearly visible from results that women belonging to the richest wealth quintile were more likely to suffer from asthma than women from the poor wealth quintiles. And they were 23% more likely to suffer from asthma compared to poor group. Similar to this, similar contrasting pattern of prevalence was found in people living in less crowded area, where women from households with no crowding were likely to have more asthma compared to the people, women living in a crowded area. Coming to the prevalence of asthma among tobacco users and non-users of tobacco, tobacco users were more likely to suffer from asthma compared to non-users. So this is the map. This is the prevalence map of asthma, where region in the dark green color depicts districts which have asthma prevalence less than 1.2%. Parrot green region depicts districts with asthma prevalence ranging from 1.21 to 2.4%. Saffron regions depicts districts with asthma prevalence ranging from 2.41 to 4.3%. And last, red regions are the ones with asthma prevalence greater than 4.31. So conclusions. The prevalence of asthma was found much above the national average for almost 1/3 of the districts in India. There is an evidence of better reporting of asthma in certain group of women, especially those coming from economically better off households. Study indicated that educational level, type of fuel used in cooking, living in a crowded area, wealth index of the households, and usage of tobacco or alcohol are some of the key risk factors of asthma. We know asthma cannot be cured, but good management with inhaled medications can control the disease and enable people with asthma to enjoy a normal active life. Eliminating or reducing these modifiable risk factors by taking up proper programs and interventions will substantially help in reducing the number of asthma cases and ensuring healthy lives and promote well-being for all at all ages. So these are the references. Thank you, everyone.
Yeah, it is time for questioning. If any questions, you can ask any participants, any attendees. Any questions?
Good morning, ma'am. I have a small question. Am I audible, right? My name is Sri Krishna. Actually, I work in a survey sector. I have an idea of how to use this NFHS data. Is these results have weighting? How you weighted these results? Are these results are weighted or unweighted results? Because in NFHS we'll get, since there are samples, we'll have weights to each and every household. It's like we are estimating, or we are just giving the sample values of the data. The question.
Sir, am I audible?
Yeah, you are audible.
Yeah, sir, these are the unweighted estimates, sir. We didn't consider the weighted weights of each household. Yeah, these are the unweighted ones.
Any more questions? Pooja, I have one question. You said you just said somewhere that in certain groups higher reporting is observed. Whether you can use that word reporting, or whether it is higher prevalence is observed. Higher reporting or
actually, higher? Okay. Actually, it is higher reporting, ma'am. Actually, because in this survey there was no proper test has been conducted to check whether they really have asthma or not. It was just a question that was asked by the surveyor. Like they have asked, so if the women knows that asthma will have these symptoms like coughing, wheezing, this problem, they will be very good in identifying. So this self-reporting will be affected by how much they have the exposure for mass media and how much knowledge they have regarding asthma, all these things. So that we could see out of all the women, there were more self-reporting from the individuals or from the group where they had a good education, and if they were coming from a better off family, so they were knowing that these are the symptoms that will lead to asthma. So there we saw higher reporting of asthma compared to the places in the groups where there was no proper education and whose wealth status was very low. So we thought even that is one of the reasons why we got asthma prevalence more in case of richest and rich women compared to the poor group. But if we consider other variables like using clean fuel and all, we can easily make out the people with less wealth definitely will be having will be using unclean fuel for cooking, and we know that that will lead to, that is one of the risk factor for asthma. So it is like self-reporting has effect on effect by this education status, wealth status, ma'am.
Okay. Any more questions?
One comment, ma'am. It's like
Yes.
We can reduce this self-reporting also by using weights. Just keep in mind, because I work in a biggest survey in Chennai, like in Tamil Nadu Household Planner Survey. So we used to work on these weights more. So you can reduce this, since you know it's a bias. You like urban areas may report more asthma cases because they have more education level. Like using this like by using this as like a dummy variable in your study. By constructing the weights, you can reduce this unbiasedness and you can get more accurate results. Just keep it.
Okay. Thank you, sir. Thank you for your comment.
Okay. Any more questions? Hello. Any more questions? Okay. If there are no more questions, we will be moving to the next presenter. Pooja, thank you for the good presentation. Yeah, we will be moving to the next presenter. I welcome Raksha Pujari, the next presenter, on the topic on two stress regular graphs. Yeah, welcome Raksha.
Good morning, everyone. I am Raksha Pujari. I am a research scholar working under the guidance of Professor K. Manjunath Prasad from the Manipal Academy of Higher Education, Manipal. My topic of presentation is two stress regular graphs. Let me begin with some basic definitions. The graph G which we have considered here is a finite, simple, and connected graph. So in any network, we can see that we can rank the nodes or edges using certain centrality measures. Basically, the centrality measure is a function which assigns a real value to every vertex or edge of a graph. In social science or in biology, we can see the application of the centrality measures. There are several centrality measures such as degree centrality measures, betweenness centrality measures, closeness centrality measure, eigenvector centrality measure, etc. So here we will be looking into a centrality measure called as stress. So given a vertex V in a graph G, stress of a vertex V is the number of shortest path in a graph G having V as an internal vertex. So if we take the sum of all stress of a vertex in a graph G, then it will give the total stress of the graph. If stress of every vertex of a graph G is R, then we call such graph as R stress regular graphs. So basically all the regular graphs are stress regular graphs, but a stress regular graph need not be a regular graph. We will see one example in this presentation. Further, if G is a R stress regular graph and if D is the diameter of the graph, then if we talk about a zero stress regular graph, then it has to be a complete graph. Because if we look at, because every pair of vertices are adjacent and therefore the stress at every vertex will be zero. Coming to one stress regular graph, a graph will be a one stress regular graph provided it is a cycle with 4 vertices or a cycle with 5 vertices. So now let us see certain observation on two stress regular graph. So if we talk about a two stress regular graph, then we cannot have a pendant vertex, because if we have a pendant vertex, then the shortest path. So in a two stress regular graph, we don't have a pendant vertex. One more thing here is, if you consider any vertex, then its neighborhood cannot be a complete graph, because if we have a vertex whose neighborhood is a complete graph, then stress of that particular vertex will be 0, and which cannot happen here, and therefore neighborhood cannot be a complete graph. Now further, as we saw earlier, if we have a two-stress regular graph, then 2 should be greater than or equal to integer part of d squared by 4, where d is the diameter of that particular graph. And therefore, if this diameter is greater than or equal to 3, then we arrive at a contradiction, because integer part of d squared by 4 will be greater than or equal to 2.25. But if it is a two-stress regular graph, this should be true, and therefore we arrive at a contradiction. And so, if we have a two-stress regular graph, then diameter of that particular graph will be equal to 2. One more thing we can note here is, in the neighborhood of any vertex, there can be at most 2 non-adjacent pair of vertices, because if you have more than 2 non-adjacent pair of vertices, then stress of that particular vertex will be more than 2, which should not be the case here. Further, if G is a two-stress regular graph, then there exists exactly 2 non-adjacent pair of vertices in the neighborhood. It's because we know that the neighborhood should have at least 1 non-adjacent pair of vertices. But since stress of this particular vertex is 2, we can say that there is another pair of vertices U and W, such that V is on the shortest UW path. But since we are in the diameter 2 graph, distance between U and W is at most it is 2, and therefore we can say that U and W lie in the neighborhood of this particular vertex. And see here is, if G is two-stress regular graph, then the minimum degree is, it is at least 3, and the maximum degree it cannot exceed 4. And this is clear because minimum degree, it has to be greater than or equal to 3, because a neighborhood should have 2 non-adjacent pair of vertices. So it follows from there. Now let us see what happens if the maximum degree is greater than or equal to 5. So suppose we have a vertex V whose degree is greater than or equal to 4. So let us take it as D, and D here is greater than or equal to 5. So as we know that the neighborhood of V should have at least 2 non-adjacent pair of vertices. So these are the 2 possible cases. So we have taken V1, V2, and V1, V3 are the non-adjacent pair. Otherwise, we have 2 completely different pair, that is V1, V2, V3, V4 are non-adjacent pair. So if we look into the first case here, okay, this is the first case. Now since stress of this particular vertex V1, since it is 2, we can say that there must be another vertex U which is adjacent to V1, and this V1 is in the shortest U V path. Now further, this U has to be adjacent to V2 and V3, otherwise stress of V is going to increase. So that should not be the case. So U has to be adjacent to V2 and V3. And now if this happens, then U has to be adjacent to all the rest of the vertices, V4, V5, so on up to VD. Otherwise, stress of V is going to increase. Now, if we do this, if we concentrate on these particular vertices, V5, V6, so on up to VD, then we have 3 different shortest paths passing through these particular VIs. Which is a contradiction, because we are looking at a two-stress regular graph. That was the first case. So considering the second case, that is V1, V2, V3, V4, we arrive at a similar situation. That means because stress of this particular V1 is 2, there must be another vertex U which is adjacent to V1, and it is in the shortest V1 path. Now this U has to be adjacent to both V2 and V3, and after that it has to be adjacent to V4, V5, so on to VD. Again, we arrive at a contradiction. And so we can say that the maximum degree cannot exceed 4. So considering all these observations, now let us see which are the two stress regular graphs. So to begin with, let us consider a two stress regular graph wherein the minimum degree and the maximum degree is 3. So to begin with, let us consider one vertex V1 and let V2, V3, V4 be the non-adjacent vertices to V1. So now, since the neighborhood of V1 should have exactly two non-adjacent pair of vertices, now we can say any one of this is adjacent. Say V3, V4 is adjacent to each other. Now, since again stress of V3 should be 2, so to balance, we have to add another vertex V5. Once we have added this V5, it has to be adjacent to V2. Otherwise, again, stress of V1 is going to increase. So like this, if we proceed, we end up getting this particular graph. If we add one more vertex here, then stress degree of the vertex is going to increase, and that should not happen here. So this is a two stress regular graph wherein the minimum degree and the maximum degree is 3. In the next case, that is when the minimum degree is 3 and the maximum degree is 4, let us consider a vertex V1 with the degree 4. Again, neighborhood of this V1 has should have two non-adjacent pair of vertex. So we again have two cases here. One is this particular case that where we have taken V2, V3 and V2, V4 are the non-adjacent pair. And in the second case, we have V2, V3 and V4, V5 are the non-adjacent pair of vertices. Looking at the first case here, since stress of V2 should be 2, and here if we observe stress of V2 is not 2 right now, so we will have to add a vertex V6 here, which is adjacent to V2. Now if we do this, this V6 cannot be a pending vertex. Stress of this V6 has to be equal to 2, and therefore it has to be adjacent to V3 or V3 and V4 both. Further, if we add one more extra vertex here, then it will violate the condition. Either the stress of these vertices will be more than 2, or it will violate the condition on the degree. So this is the graph which is satisfying all the conditions. And here we can see that this graph is not a regular graph, but still it is a stress regular graph. And coming to the last case, and this is the graph what we have taken. Once again, to balance the stress here at this particular vertex, we will have to add a vertex V6. So in that case, this V6 has to be adjacent to V3, V4, and V5. Resulting graph is given here. And this is again a regular graph. So finally, we can say that these are the 3 two stress regular graphs. And one more thing we can observe here is all the two stress regular graphs are having 6 number of vertices. That's it. These are the references. My acknowledgement to Professor S. Armugam from Amrita Vishwa Vidyapeetham, Coimbatore, and Dr. Arati Bhatt from MIT Mahe, Manipal. Thank you for the opportunity.
Okay, thank you, Raksha. Now it is time for questioning. Audience, please ask questions. Any questions from the audience? Okay, if there are no questions, we will be moving to the next presenter. Thank you, Raksha. It was a good presentation. Thank you.
Thank you.
Okay. So now we are moving to the next presenter, Umashankar. He is presenting the topic, a note on reverse order law for outer inverse. Yeah, it's time for Umashankar.
Hello everyone, myself Umashankar Kedattaya, pursuing PhD under Dr. K. Manjunath Prasad Karanta, Professor of Mathematics, Department of Data Science, PSPH Mahe Manipal, and is also the coordinator of CARAMS Mahe Manipal. The topic of my talk is a note on reverse order law for outer inverses. These are the contents of my talk: abstract, followed by preliminaries, introduction, reverse order law for outer inverses of elements from associative rings, and references. Abstract. It is well known that AB inverse is equal to B inverse A inverse whenever the matrices A and B are invertible. This property is known as reverse order law. The reverse order law in the case of Moore-Penrose inverse, group inverse, and Drazen inverse have been investigated by several researchers. So you can refer the references 1, 3, 5, and 6. We shall discuss reverse order law in the case of outer inverses when the elements are from associative rings. We note that the class of all outer inverses of AB is contained in class of all B equal A equal. This holds in general. In the present talk, we shall focus on the conditions for the other inclusion to hold. Preliminaries. Given an m by n matrix A over a real field, consider the following matrix equations. They are called Penrose equations. The first one is AXA equal to A, XAX equal to X, AX whole transpose equal to AX, and the last one is XA whole transpose equal to XA. If A and X are square matrices, we consider the following equations in addition to the Penrose equations. That is, there AX equal to XA and XA power K equal to A power K, where K is some positive integer. If a matrix G satisfies the equation 1, then it is called generalized inverse of A, denoted by A minus. If it satisfies 2, then it is called outer inverse of A, denoted by A equal. If it satisfies both 1 and 2, then it is called reflexive generalized inverse, denoted by AR minus. If it satisfies all the Penrose equations from 1 to 4, then it is called Moore-Penrose inverse of A, denoted by A dagger, and it is unique whenever it exists. If it satisfies the equations 1, 2, and 1D, then it is called Drazen inverse of A, denoted by AD. So now we introduce minus partial order. Given rectangular matrices A and B, the matrix B is said to be dominated by A with reference to minus partial order, denoted by B less than or equal to A under minus partial order if there exists a generalized inverse GB of B such that BGB is equal to AGB and GBB equal to GBA. Introduction. We know that for invertible matrices, the reverse order law holds. That is, AB whole inverse equal to B inverse whenever A and B are invertible. So this is called reverse order law for ordinary inverses. It is well known that the reverse order law does not hold for various classes of generalized inverses. So for example, in this case, we are discussing about Moore-Penrose inverse. If A is equal to the vector 1, 0 and B equal to the column vector 1, 1, then the Moore-Penrose inverse of AB is 1. But whereas B plus A plus, that is equal to 1 by 2. So AB whole plus is not equal to B plus A plus. So reverse order law doesn't hold in general for Moore-Penrose inverse. In 1966, T.N.E. Greville gave several equivalent forms of a necessary and sufficient condition for the reverse order law for Moore-Penrose inverse to hold, and examined the nature of matrices satisfying the same. This is a classical result from the same paper. If A and B are otherwise arbitrary matrices such that AB is defined, then AB whole plus equal to B plus A plus if and only if both the following equations hold. A plus AB B star A star equal to B star A star, and B plus A star AB is equal to A star AB. If both of them are satisfied, then it is equivalent to say that AB whole plus equal to B plus A plus. That is, the reverse order law holds for the Moore-Penrose inverse. That is, reverse order law for Moore-Penrose inverse holds if and only if column space of B star A is contained in column space of A plus, that is same as column space of A star. Okay, and column space of A star AB is contained in column space of B. Okay, this result was extended to linear bounded operators on Hilbert spaces by Izumino. We can refer the reference number 4. In 2019, Dragon and Nebotsa explored new results related to the reverse order law for Moore-Penrose inverse of operators on Hilbert spaces. Wang and others presented some of the equivalent conditions for the reverse order law for Drazen inverses in the context of operators. So now reverse order law for outer inverses of elements from associative rings. Let R be an associative ring. An element A in R is said to be regular if there exists an element B in R such that ABA equals A. That is, B is the generalized inverse of A. So if there exists a generalized inverse of for A, then we call A as regular. In this case, B is said to be the generalized inverse of A. Okay. An element C in R is said to be an outer inverse of A if CAC equals C. Further, B is called a reflexive generalized inverse of A if it is both the generalized inverse of A as well as the outer inverse of A. An arbitrary outer inverse of A is denoted by A equal, as in the case of matrices. Minus partial order has been defined using generalized inverses on class of regular elements in any associative ring as in the following. For any regular elements A and B in R, the notation less than or equal to minus defined by A less than or equal to B under minus partial order if there exists a generalized inverse GA of A such that BGA equals AGA and GAB equals GAA. In which case we write A is less than or equal to B under minus partial order. Now we come to the core part of this presentation. Note that AB whole equal into A, this will be an outer inverse of B because AB whole equal into AB equal, that will be AB equal into A. So that is nothing but AB equal into A, and B into AB equal AB equal, the last part is AB equal, so this will be B into AB equal. So AB equal into A is an outer inverse of B and B into AB equal is an outer inverse of A. And hence we can say that AB equal, this is equal to AB equal AB equal, that is true in general, that is equal to, I can split these terms as AB equal A into B into AB equal. But we have seen that AB equal A is an outer inverse of B and B into AB equal is an outer inverse of A. Therefore, AB equal, so I have written AB equal as an outer inverse of B into an outer inverse of A. Thus, the class of all AB equal is contained in B equal, a class of all B equal A equal. So this holds in general. Now we have to search for a condition when other inclusion holds. That is, class of all B equal A equal is contained in class of all AB equal. So let us see when it happens. Is there such a condition? Well, we claim the following. If GB and GA are outer inverses of B and A respectively, then we note that if RGB, that is the left ideal of GB, is contained in RA1, where A1 is AGAA, okay, that will be less than or equal to A under minus partial order, or if GAR is contained in B1R, where B1 is equal to BGBB, which is less than or equal to B under minus partial order, then GB into GA is contained in class of all AB equal. Okay. So just one line proof for this. We are using the fact either this or this. Okay. So in fact, GB, GA, AB, GB, GA, that will be equal to, if I use GAR is contained in B1R, then GB, GA, AB, GB into GA will be B1 into some element from the ring. That is B1 is nothing but BGBB. So GB, BGB will be GB. So we are left with GB, GA, B, GBR. But BGBR is nothing but GA. So we get GB, GA, GA. So which is equal to GB, GA. Similarly, if we use this fact on the right, that is RGB is contained in RA1, then also we will get the same. Thus, class of all GBGA, that is outer inverse of B into outer inverse of A, that is contained in class of all AB equal, class of all outer inverses of A. Okay, these are my references. Thank you so much.
So now it is time for questioning. Audience, please ask questions. Any questions? Okay, thank you, Shankar. I think there are no questions. Thank you for the good presentation. Thank you all.
Thanks a lot, ma'am, for joining us today. So next session will start exactly at 12 o'clock.
Prasad, can I talk? Prasad?
Tell me.
Why I'm seeing, so yesterday I see two windows. Like, do you hear me now?
I can hear you with some break.
And what about my video?
Yes, you are visible, sir.
Now you are visible. Yes.
So this is the best I can do, because yesterday I had some problem in the inauguration. I was seeing 2-3 windows. I don't know what was. But is this okay now? Because this is the way I will connect tomorrow maybe.
Yeah, it's fine. You are clearly audible.
But sometimes I see 2 windows, so I don't know which to join. And now I'm seeing only 1 window.
Yeah, this is perfectly fine.
It's fine. Okay, okay.
Yeah, yeah. Even I heard lots of complaint on this our Teams software itself.
Right, it is a problem. Team software. I think it is best to copy. I think clicking on the link is not a good idea. What you should do is you should copy the link in the Firefox browser or some browser. Because if you click the link, it goes to that Opera browser. That is not very good.
Okay.
You can advise people to copy the link and paste it on a suitable, either Firefox or Google Chrome, whatever.
Okay.
That seems to work better, at least for me.
We are having this Google, and automatically it goes to this one. So you are not finding much of a problem.
Yeah. So there are some changes, right, in the schedule?
Not much. Let me recall.
Because today Raghavan stock was there, but that was switched to somebody.
No, that is for our consumption only.
Oh, okay.
That is for our consumption. I did not send it to the.
But there is no change in tomorrow's program.
Earlier, Balakrishnan was not available. No, when I heard that news, then I had very lesser time, and that's what the change I made. But today, Professor Arne came, and he gave consent. You attended that one? Yeah. So he gave a repeated talk at the same time. So we didn't make use of Raghavan's lecture.
Okay. Okay. Everything fine?
Today it is somewhat better than yesterday. Yesterday we had gone through some little bad experience.
Yeah. Okay.
Okay.
Okay. I'll connect tomorrow for my chairing, but I'll connect afternoon also some talks maybe.
Okay. Tomorrow we will have a very short inauguration, almost informal kind of inauguration.
Okay.
Okay, we'll meet. Welcome, Martin.
Thank you very much. We start in 10 minutes, right?
What time it is? Early morning?
It's 7:30 or 7:20.
Very early.
So I just sent away my 2 girls to school.
Okay.
But we start in 10 minutes, right?
Yes.
Yeah.
We'll start in 10 minutes.
And now
the arrangement was
Kasha first.
Yeah, Kaziana will be coming first, I think.
Yeah.
Katarziana, sorry, I spelled wrong.
Kasha first and then Simo after that.
Yeah, Simo will come later.
Yeah.
Today is better day without any much problem. Yesterday we missed Augustine for some time.
Yeah. So a year ago, I thought it was really should be possible to travel to Manipal this time of year.
Yeah, I was expecting you all.
Yeah, but this pandemic driving us all crazy, I guess.
With that expectation, we are posted by 1 year, but it is of no use.
No. It's very strange. I wonder how long this will take before we can start to travel again. if ever. But I guess I hope so.
Maybe we'll consider this as the norm of the day and ignore.
Yeah. I read in the Swedish newspaper yesterday, there were some researcher who said what we all have said, that all will we get COVID. It will not disappear. It will stay there forever. So somehow we have to start to learn to live with it in one way or another. But now it seems that, at least here in Europe, it seems that it's coming back. Not Sweden is quite okay so far, but we have had our first waves with it, so I guess we are in that a better position.
We are also quite tensed about the new Omicron variant.
Yeah. Exactly.
Maybe we'll treat all this as another type of common cold and ignore. Yeah, we may come across such day.
Yeah.
What about Simo? Simo is here around?
Moment. I'm admiring you there.
Yeah, in fact,
you guys are like Netflix stars. I have taken several screenshots of you to be circulated. I can tell you that the COVID contamination figures over the last few days in Finland, they have been the worst ever in Finland. So this is, I entirely agree with your concerns that you mentioned 2 minutes ago in your mutual discussion, which I was following from Nokia. But it's unbelievable. It's unbelievable.
That's the thing when you are in a Teams or Zoom or anything, and there is just only two having video on, and they talk, and they don't take notice of how many others there are as well in the listening to the discussions. No, but you have the feeling that only two, and then you realize there's maybe 100 more listening to you.
You remember the old good times when the men were very careful about their dressing when they had a performance. They were the shirt was should be closed, and all details of clothing should have been okay. Now nobody even knows if we have trousers.
Exactly. Oh, that's how it is.
So, but what is interesting that your picture quality in both cases of yours is really very nice.
Yeah.
Very much it's due to your personal attractiveness, of course. But of course there is some technology which so it works very nice. I have a relatively big screen. But if I could also watch this from television, and then it would be even bigger and bigger. Your heads would be 1 meter by 1 meter, maybe.
Yeah.
But at the same time, you could be followed in a cell phone.
Exactly.
1 centimeter per person.
No, it's really.
Timo, you happen to be a good photographer, but you'll have to manage with only screenshots.
Yes, now that is correct. I have had to make a change to move only to screenshots. So Kasia is performing first.
Yes, yes.
Maybe she is watching us.
Yeah, you never know.
I'm sure she's watching us. Maybe you should invite her.
Yeah, right. Pooja or Uma Shankar, please bring her in case she is there around.
What do you have, by the way, Martin, as a background? Do you have a regular wall?
Yeah, this is my basement.
Yeah, you have to behave well and you get out in 2 years.
It's not so fancy.
But it is somehow very artistic and yes, no reason to complain.
No. Sometimes I can show you. Sometimes I use this one instead. Like this, I guess.
Ah, I see.
This is Rwanda.
I see. Yes, I should take my Rwanda zebra pictures.
Exactly. No, otherwise this is my, as you can see, this is my regular basement here with I have some fabric hanging, so I can just hide everything that I don't want to show.
Ah, yeah, I see.
You know, my wife is working at the competitor to Nokia once a time. She's working at Ericsson.
Yes.
And she has been sitting home now, working from home more or less 100% since March 2 years ago.
Yes. That puts the marriage to a test.
Yeah. So she has been working from here many hours here from the basement.
Yes, it is unbelievable.
Yeah. Well, now Kasia is here as well.
Yeah, it seems Katarzyna came in.
Yeah. Good morning, Kasia.
Good morning, everyone from Poland. We have early morning, in fact. My family is just leaving to school. Yeah. They are going to school, to work, and so on. So still a bit of mess around.
Yeah, exactly the same situation as here.
Yeah.
Actually, I can just tell you all that I just invited Kasia to Linköping for 2 weeks, doing research in February. So she will come to Sweden. Yeah.
I hope COVID will allow us to meet in person.
I really hope.
Yeah.
Otherwise, you will be in 2 weeks quarantined.
Yeah, exactly.
Yeah, the question how it looks like in Sweden.
But it's 2 weeks in basement, nothing else.
Exactly.
Yeah, but you know, in Poland, if you are on quarantine, you cannot leave your house. But everyone can come to visit you.
Mm.
So that's extremely strange.
Yeah. In Sweden, there is no rules. There is only recommendations. So you're recommended to stay home, but you're allowed to leave and you're allowed to do. I even don't think. Maybe we have a quarantine if you have been traveling from outside European Union. Otherwise not.
Very good.
Yeah.
Lucky you.
For the moment, I must say.
Yeah.
You never know.
Well,
you never know tomorrow what happens.
You have a lot of freedom in Sweden.
We have
with respect to all those rules. Here is not so easy life. No, if you are vaccinated, you are not going to quarantine.
Okay.
So that's okay. Oh, my husband is saying it's not anymore.
No.
Okay, it is 12 o'clock now.
Yep.
Shall we continue the session now?
Yes. So
Raksha, please.
Yes, sir. Welcome back, everyone. It's my pleasure to invite the speakers of this session. We have with us Dr. Katarzyna Filipiak, who is from Department of Mathematical and Statistical Methods, Poznan University of Life Sciences, Poland. Her research interests are experimental designs, optimality of designs under univariate and multivariate linear models, optimization of some specific functions of eigenvalues of semi-positive definite matrices, etc. She has organized many conferences and workshops and has delivered invited talks in several conferences. Today she will be talking on Frobenius norm, entropy and quadratic loss functions as the measures of discrepancy from structured matrices. Welcome you, ma'am. Also we have with us Professor Simo Puntanen from Tampere University, Finland. He is a senior researcher of the Academy of Finland from 1992 to 1995. His main research interest lies on matrix methods in statistics with particular emphasis on linear statistical models. He has served in scientific organizing committees of 65 conferences and workshops. Jointly with Professor George Stan, he is a founding member of the series of international workshops on matrices and statistics. He is closely associated with CARMS. Today he will be talking on the topic a review of the linear sufficiency. I now request Professor Martin Singal from Linköping University, Sweden to chair this session. Over to you, sir.
So thank you very much, Raksha. So it's a pleasure to share this session with two friends of mine, old friends, I think many years back in time. So the first speaker is Katarzyna Filipiak from Poznan, and she will talk about, as we heard, Frobenius norm, entropy, and quadratic loss function as the measure of discrepancy from structured matrices. So please, Kasia, or please Raksha, to start the video, and then afterward we have the discussion.
Ladies and gentlemen, welcome everyone on my presentation. I would like to thank the organizers for the possibility of presenting the material, my results here. I'm going to talk about some statistical problem related to testing hypothesis about covariance matrix structure, especially about the power. So, as one can remember, the power of the test is the probability of rejecting null hypothesis when the alternative is true. So the thing is how to measure the power, how to measure the probability, because if everyone can know that the power of the test really depends on how far we are with alternative hypothesis from null hypothesis. But let's start from with the formulation of the problem. We have three features, we observe three features in two time points. And we have an individualized disposal. So we are measuring, for example, key characteristics and three time points for n patients. We will assume that yi are our observation matrices, which are normally distributed. So each yi is Q by P matrix with some mean vector, a mean matrix M, and with some matrices sigma and psi, which are dispersion matrices of time points and with of features, which are well, this is sigma is for rows and psi is for columns of this observation matrix Y. So after vectorization, we can also present that model in a vectorized form. Vectorization, just to recall, is arrangement of columns of a matrix one under the other. So we can also vectorize the matrix M, expectation matrix M, to get vector mu. But the covariance matrix become a canonical product of two matrices, two dispersion matrices. This one was for rows, and this one was for columns. So as you can see, this canonical product structure is very natural for such doubly multivariate observations. So how many parameters we have to estimate here are unknown, let's say. P plus, both of them are symmetric, both of them should be positive definite. So we have P plus 1 over 2 elements here inside. We have Q plus 1 over 2 elements in sigma. And to keep identifiability of this canonical product, we have to fix one element of one of those matrices. So that's why we have to add, we have to subtract one from this number. Okay, when it is possible to estimate, when we have a guarantee that this matrix is positive definite, if the sample size is higher than maximum of the dimensions. So a maximum between P and Q, number of characteristics and number of dimensions. However, in general, we might say, if we do not know anything about the structure of covariance, we may write the general model in the following way, where this omega will be general constructed matrix, just symmetric, just positive definite, which is of size of order Q. In such a case, the number of unknown parameters is definitely higher than in psi times sigma, because we have PQ plus 1 over 2 elements. And this number increases rapidly with the size of Q or with the size of Q. So to guarantee positive definiteness of this omega matrix, you have to have the number of individuals, the sample size, higher than PQ. So if we compare those two conditions, and higher than maximum of the dimensions and higher than the product of the dimensions, we can easily observe that special covariance structures, some analysis can be easier, or we will get more degrees of freedom for estimation of main parameters, let's say related to expectation. However, we are in fact interested in the hypothesis if our data really has that separated structure. So we are interested in the following hypothesis. In null hypothesis, we have just a structure, but this is nothing specified. This is arbitrary symmetric positive psi matrix and arbitrary symmetric positive definite sigma matrix versus alternative in which omega is the structure. The test which serves for testing such a hypothesis, the most common, let's say, is livelihood ratio test and is the Rao's score test. In both of the tests, the matrices with heads appear. It means that because usually, of course, omega and psi and sigma are unknown, there are the estimators of them, and there are maximum likelihood estimators. And our aim will be to compare those two tests with respect to the power. However, to compute the power, as I mentioned at the beginning, we need to know how distant are those two hypotheses. How far from each other is some arbitrary matrix omega? How far is arbitrary omega from the set of separated structures? The problem is that, well, there are two problems. One problem is what should be the function which measures this distance. And second problem is how this set of canonical product can be presented. And now I will show you a graph, and I will show you that definitely is not any kind of surface, a flat surface which we can imagine. It's quite difficult to imagine. Why? For example, because of the geometry of the space. Note that if we will choose two arbitrary matrices sigma, and we will choose a single psi, And if we will take a Kronecker product, let's say this red point is psi 0 times sigma 2, and this red point is psi 0 times sigma 1. And if we are going to add those 2 points, those 2 matrices, then we will obtain a point for psi 0, so it will be in the same line, let's say, and line I will say in accents, because it will be something like psi 0 times sigma 1 plus sigma 2. So it's nothing like standard geometry of summing two vectors to points. Moreover, what will happen if I will choose arbitrarily 2 matrices psi 1, psi 2, and sigma 1, sigma 2? If I will add those 2 points, let's say those 2 vectors, I will get a point which does not belong to the space generated by Kronecker products. Because everyone knows it is very easy to verify that if we will add 2 Kronecker products, we do not get a Kronecker product anymore. So in fact, if we will choose arbitrary Kronecker product, and if we will add arbitrary matrix which does not belong to this space, we will also get the point, the resulting matrix will be not in the set of Kronecker products anymore. So how to define the distance between matrix which is out of the set of Kronecker products, and how to determine the point, the Kronecker product, which will be the closest. One of the most intuitive methods is to choose arbitrary matrix, arbitrary Kronecker product psi times sigma, and to choose to generate one single matrix V. About this V matrix, we know that this is completely arbitrary symmetric matrix. And what with that? We will choose some number lambda, one parameter lambda, let's say, which will be responsible for our distance. So V will be the same, but for lambda equals 0, we will have exactly the structure. So the distance would be 0. If lambda would be 1, for example, then we are getting a matrix omega, which is distant at 1, and so on and so on. So this is very, very intuitive method. However, it has 2 serious disadvantages. The first one is that if we will choose different V matrices, even the domain of lambda, which guarantees positive definiteness of omega, is not the same. So lambda equals 1 for one V matrix will be completely different than lambda, well, for one V, lambda can be, for example, only positive. For another one can be only negative. For another one can be from, let's say, interval from -1 to 100, and so on and so on. Everything depends what we will choose as a V. Another thing is that lambda for different V's are completely incomparable. So for one V, lambda equals 1 does not mean the same as lambda equals 1 for different V. So to avoid this problem, we propose some naive method, let's say, so a modification of this intuitive method. So what we are going to do is to choose the following combination of this Kronecker product and some arbitrary V. So V still is arbitrary, but now lambda belongs to 0, 1 interval, and now the distance between omega and so this whole matrix and the set of Kronecker products will be measured by this lambda. So we avoid here this problem with the domain of lambda, because now lambda is always from 0, 1 interval. However, still for two choices of V matrix, these distances are not comparable. So we can look on the graphs of the power which we simulated. So the first row is for likelihood ratio test, the second row is for row spot test. And the blue line represents the power for one matrix B, and the red one represents the power for the second matrix B. And for all the cases, this lambda parameter, which measures the distance, is equal to 0.01. So as we can see, for the same distance, we should have the same power, which is not the case here. So we may see, okay, this intuitive or this naive approach is not suitable if we are going to measure the power of the test. So what to do next? Let's imagine that again, like a surface. We are going to measure, we have some arbitrary matrix omega, which was not created like a sum of a Kronecker product and some matrix, but some general arbitrary generated matrix omega. And how, the question is how to measure the distance. So again, according to intuition, one would say, okay, let's take and project this omega for the space. But so let's take a Frobenius norm. So, okay, what will happen if we will choose this function, this measure like Frobenius norm? So we have to minimize, we have to find the minimum of the trace of the following square difference of matrices. So first problem is how to get the minimum. So Van Loon and Pizzianis in 1992 formulated the following theorem in which they determined the solution. They found that the minimum, respectively using some eigenvectors and eigenvalues. However, note that this discrepancy, this Frobenius norm, is not upper bounded. So it would be good to normalize it. So to get this zeta in the interval 0, 1, we will operate with eta index, which will be zeta divided by trace of omega squared. So what then? Let's see if for the same distance eta, but for different omegas, we can find that the power will be the same. So again, we made a simulations. We choose two omega matrices, and both of them are distant from the set of Kronecker products by 0.1. And as you can see, again, the powers are completely different. So the conclusion is Frobenius norm is still not good to measure discrepancy. So what can be other function? By the way, there is another disadvantage of this Frobenius norm. Look that now I choose this again two omega matrices, but one omega is distant by 0.1, and the second one is distant at 0.5. So power should be higher for this blue matrix, let's say. If the hypotheses are more distant, then the test should detect that the alternative is true more often. But what is the case here? Here everything is okay because the blue line is above the red one. But look, if we took P and Q equals 3, then it happens that the power is higher for matrices which are closer. So this is definitely how it should behave. So Frobenius norm will definitely be not a good measure. So let's now consider entropy loss function as the discrepancy. Entropy loss is defined as follows, and we are looking for the distance, we are looking for the minimum of the following function. Again, since this upper, okay, so how to find the minimum? In the paper from 2021, we gave that solution, we gave that minimum, and again, since this discrepancy zeta is not upper bounded, we will normalize somehow. We will concentrate on adjusted discrepancy, which will be in 0-1 interval. Okay, and what then? Now look, we have completely nice graphs, completely different than previously. We choose now again 2 different omegas, which does not have any structure, which are distant from the set of chronometer product structures by 0.1. So look, then this is of course by simulation, so there can be a little differences. But look, that in general, both functions behave the same. Okay, so what if I will compare 2 matrices which are not equally distant, but for which one distance is higher than the second one? So look here, for distance 0.5, we have higher power than for distance 0.1, so everything is correct. So the first conclusion is, okay, empirical, entropy loss function can be used for measuring discrepancy in power comparison. Okay, so another thing, quadratic loss function. There is another function which is quite popular, quite known in statistics, and has the following form. And again, we are going to minimize it through psi times sigma, because we are looking for the closest point from the set of chronometer products. The minimum of this function is not so easy to get. However, it is possible numerically to solve the system of equations. And again, since this is not upper bounded, we will use some adjustment. So now we know that eta distance will be from 0,1 interval. And what will be related graphs? If we will choose again omega 1 and omega 2, which are distant with the measure which is based on quadratic loss function by 0.1 from null hypothesis, we again are getting almost the graphs which almost overlaps. So we also can, in fact, recommend this quadratic loss function for measuring discrepancy. Let's check, just to be formal, what is different discrepancies. So similarly, as in the case of entropy loss, we have higher power for higher distance. So as a conclusion, we may say that okay, Frobenius norm and this intuitive method or naive method are not suitable, but entropy loss and quadratic loss, they are. Let's also look for some known results. In 2004, Lu and Zimmerman tested this hypothesis. However, they didn't know how to measure the power. So they created just a single alternative. So they based on the chronometer product of the following form. So very, very simple matrices. They choose raw from the following set, and they distinguished 4 types of modifications, 4 types of alternatives. In type 1, they are just changing one diagonal element. In the second type, they are changing this one, let's say, of diagonal element. From the symmetry, they have to change, of course, both. In type 3, they change this element, and in that type 4, they change, let's say, 4 elements. And the question is, what will happen with the power? So they calculated the power of likelihood ratio tests, and they presented. They also, we did the same for round score test. And of course, I will not keep your attention for the case because it's not important. The important is what will be if we will try to take all those matrices, all those 4 types together to see what is going on with the power according to respective measure of discrepancy. So look, but if we choose a Frobenius norm as discrepancy, then we have a mess. But if we have entropy, if we will get entropy loss function as discrepancy, then we can see that for bigger changes, let's say, for increasing discrepancy, also the power increases. This is for RFT and this is for RST, especially if we have relatively high sample size. So this is very, very good result. We do not need to consider those 4 types separated. We can combine them together. What was quadratic loss function? Very, very similar behavior. So summing up, naive method does not work well. As for the same discrepancy, the power of test depends on chosen matrices. Frobenius norm does not work well. As for the same discrepancy, the power of test depends on chosen matrices. Moreover, for higher discrepancy, Frobenius norm indicates lower power of the test. But luckily, entropy and quadratic loss function works well for both tests. And one more comment related to the way of determining the minimum of the function. For entropy loss function, also this solution, let's say, is numerical, however, is a bit quicker to solve respective system of equations. So if I would recommend one of those functions, then I definitely would recommend entropy loss function. Okay, and I'm almost finishing, but I wanted to pay your attention also for another thing. Here again, I present the form of likelihood ratio test and Rao's score test. It was on one of the first slides. And since the entropy loss function and quadratic loss function was so good, so I'm representing it also here. So entropy loss and quadratic loss. So know how similar they are. What's the difference? The scalar at the beginning and the role of Kronecker product and omega. Always I can switch the order. However, here, for example, in LRT, we have to inverse Kronecker product, while in entropy loss, we have to invert omega. The same with RST. In RST, we have to invert Kronecker product, while in quadratic loss function, we have to invert omega. Yeah, everything is correct. Here there are different matrices because they are in different way different. Okay, so our point was perhaps there is some kind of relation between the way of measuring discrepancy and the way of testing. So our suppose was that if we are using IRT and if we are using entropy loss function as the measure of discrepancy, then the power of IRT will be higher than of RST. And opposite, if we will use quadratic loss, then the power of RST will be higher than LRT. And we made some simulations, we made some comparison, and we got the following. In this case, LRT appeared a bit better than RST, but it's not the rule. And the question is, what was the discrepancies? The discrepancy for entropy loss function was 0.37. While the discrepancy for quadratic loss function was 0.5. So if there would be any relation between discrepancy function and test, then the relation should be opposite. So here, this graph, let's say, contradicts that suppose. So thank you very much for your attention, and I'm waiting for questions at the end of some comments. Thank you, Mr.
So thank you very much, Kasia, for an interesting talk that I guess we will discuss later on when we meet again. It's very
I must say that I was on another conference when I recording that, and I was extremely tired when I did it.
No, it's very important how you do this. I have done this many times, not for this with the Kronecker structure, but also when you do other multivariate tests, and then you need to find I mean, in the univariate case it's very simple, but in the multivariate case it's not so simple how you measure how far away you are from the null hypothesis.
Well, but it's also not a case in, well, let's say, univariate case. Univariate, I mean, in standard multivariate case, right? If you have structured matrix, This is really difficult.
Yeah.
And we know that Anthropos, that Frobenius norm does not work.
No.
Moreover, Anthropos has some statistical meaning, right? This is the discrepancy between two distributions. Frobenius does not have that meaning.
And this is exactly what I mean. In the univariate case, it's straightforward to do this, but in the multivariate test, it's not. Even if you don't have the Kronecker product, you can just have a test on covariance matrices or whatever. So any questions for Kasia or comments? No question and comments. We can come back to that later after Simon's talk as well. So thank you very much, Kasia.
Thank you. It was a pleasure to be there.
Yeah. So the next speaker in this session is Simo Puntanen from Nokia in Finland. I was wondering when we met last time, but I guess we met. I mean, we met 3 years ago in Manipal, and we had a very nice week there. Even if my week ended up with some problem with my stomach, but then Simo could give me some very good medicine that he got from his doctor. So I was hesitating before I took them, but I took some pills and then I was fine after that, before my flight back home to Sweden. But then I guess we also met at last IWMS in Shanghai.
Yes,
when I also met Prasad for the last time we met also. So now today we will listen to Simo and he will talk about a review of the linear sufficiency. So please, Simo.
Yes, please play Elvis.
Yeah, please play Elvis. Good.
Good morning, everybody. This is Puntanen, Simo Puntanen speaking. And I will speak about linear sufficiency. It's a review kind of paper, but there is also something new. Let me clarify one thing that this time you are unable to interrupt me because this is a pre-recorded session. This is joint work with Steve Haslett, Jarkko Isotalo, Radek Kala, and Augustin Markiewicz. Here is the group photo of Oceans 5. It is a quite nice group, I must say. The talk is based on a recent paper which appeared in a Springer book that came out some weeks ago. The paper has 49 pages. It's a relatively long paper. These are question marks if somebody is surprised what he's seeing. And here are 3 models or equations. The first one is the standard linear model y equals x beta plus epsilon. Beta is a fixed but unknown vector. Epsilon is random error. Y is observable. If I pre-multiply this equation by the matrix F, I obtain the transformed model T. And the third line here is describing how the new observation is believed to come up. Y star is the new observation. We don't observe this guy, but we want to predict it. Now when we have these 3 equations or models, the linear sufficiency joins the game. The concept of linear sufficiency was essentially introduced in early 80s by Paksalari, Kala, and Rygas. Radek Kala, Jerzy Paksalari, and their papers appeared in Annals of Statistics and JSPI and Sankhya. Here are the front pages of each of these papers, and I promise you I will go through every line of these papers. You will definitely not get bored. Linear model introduction. It is the standard linear model y equals x beta plus epsilon. X is a design matrix. Y can be observed. Beta, we want to estimate. Epsilon, random error. Y star here denotes the unobservable random vector of near future observations. It is believed to come from this equation y star is equal to x star beta plus epsilon star. Beta is the same as in the standard linear model. X star is given. Epsilon star random error unobservable like y star. So in this situation, the expected vector of the long vector y star is x beta, x star beta here, and the covariance matrix of y star is gamma. The essential thing here is this covariance matrix between y and y star. That we assume that gamma is known, but particularly y gives us some information from y star through this cross covariance matrix up here. For brevity, we can denote use this triplet notation about this linear model, where we have also new future observations. And some words about blue and blob. If GY is a linear unbiased estimator for estimable mu star, which is x star beta, then it is the equation gx equals x star. That is then holding. That guarantees that the gy is a linear unbiased estimator. And here is an encouragement for myself, saying that I could as well jump straight to the page 21, because this is very well-known stuff. What are the next 6 pages? So blue and blob. If GY is a linear unbiased estimator for x star beta, then Gx equals x star. I apologize for coughing, but thank God you are far away from me. GY is the blue if the covariance matrix of GY is the smallest among all linear unbiased estimators. And the linear unbiased predictor is defined in the corresponding way. AY is linear unbiased predictor if AX is X star. And now AY is the best linear unbiased predictor if the covariance matrix of the prediction error y star minus AY is below the covariance matrix of the other prediction error y star minus dy. If this is minimal, we are minimizing the prediction, the covariance matrix of the prediction error. So AY in blob case, it provides the minimal covariance matrix for the prediction error. If we denote by M the matrix I minus Px, Px is orthogonal projector onto the column space OX, we have convenient notation which makes life easier, but one has to remember this for a while. What is the meaning of, of the matrix M? As a result, we get three equations, and they are fundamental equations for getting blues and blobs. For example, the second equation here, what is its meaning? It tells that if B satisfies this equation, then By is blue for X star beta. And the same concerns these other equations. And often this is called the fundamental blue equation. And this has always a solution when X star beta is estimable. If you look at these equations, it is the XVM part here. That is the same in all three equations. But the right-hand side of these equations is different. Now we can go to linear sufficiency. A statistic Fy is linearly sufficient for mu star, which is X star beta, if there exists a matrix A such that A Fy is the blue for mu star. A short notation is this Fy belongs to S mu star. What this means is that if we multiply the response Y by matrix F, we get Fy. We can obtain the blue for mu star by A Fy for some A. We don't lose anything essential if we do this transformation for the response variable. We can still, after that multiplication, we can get the blue. So that's the meaning of the linear sufficiency. And the linear sufficiency for predictors is defined in the very same way. If we have a matrix A such that A Fy is the blob for Y star, then Fy is linearly prediction sufficient for Y star. Then lemma 1 is concerns the set of matrices script W. It is a set of matrices which are of the form V plus X U prime X prime, where U has such property that the column space of W is the same as the column space of X V. So this is an important set in what is coming. Now in this situation, the following statements are equivalent. Fy belongs to this class Sx star beta. That simply is telling that Fy is linearly sufficient for X star beta. The second condition B, it comes automatically from the column space condition for this particular equation to be consistent. But the property C, which is equivalent to these two, that is not so easily available. That was introduced by Baxalari and Kala in 86. If we put X star equal to X, then Fy is linearly sufficient for X beta if and only if the column space of X is a subspace of the column space of W F prime. These were the linear algebraic characterizations for linear sufficiency. Now here is the transformed model. We are pre-multiplying the original model by matrix F. Notice that F has n columns, but the number of rows is variable. It can be. It is what it is. Now, and we will play with the connection between the original model and the transformed model. And here is one crucial lemma concerning blues of mu star under original and under the transformed model. Mu star tilde is the blue under the original model. And then this lemma says that Fy is linearly sufficient for mu star if and only if the blues of mu star under the original model and the transformed model are the same. And formally one should add for equations like this the statement that this holds with probability 1. And this is further equivalent to equation between the covariance matrices of blues under these two models. Then some words about the representations for the blues. Mu tilde denotes the blue for x beta under original model, mu tilde t in the transformed model. If G is chosen, as in the first line here, W is taken from this script W class, then GY is blue for X beta in the original model. That's from CRO 50 years ago. In the transformed model, we have to have mu X beta estimable under this. That is required, of course. Now, if that is true, then C times Fy. Fy is response in this model. C times Fy is blue for X beta in this under this model if C satisfies the fundamental blue equation, which is tailor-made for the transformed model. Here is covariance matrix. Here is the Fx perp, so to say, this green matrix, and Fx is the design part from this model. So C can be solved from this equation. And here is one presentation for, this is one expression for C that is not difficult to obtain at all. This is the multiplier for Y in the transformed model to obtain the blue for X beta. And now we go very quickly through this section number 5, because it is not so interesting. It's difficult to follow to get the idea of what's going on. But let's have a quick try. Y star tilde is denotes the plop for Y star under the original model, and YT star tilde is plop in the transformed model. So that's notation epsilon, the same thing. For epsilon, we calculate the plops. And then one can simply calculate and express these blues and their covariance matrices in this form. But as said, it's not possible to get much meaning to these formulas during this short time. We assume that mu star X star beta is estimable under M and under T, and this this has to hold, otherwise we can't have any progress. So X star has to be of the form LFX for some L. And therefore mu star is of this form. This is of importance, but let's have a second slide today, and this gives the expression for the blob or Y star. We are predicting Y star, and it has this kind of explicit expression. The formula A is easiest to interpret. It tells that the blob or Y star, which we want to predict, it is equal to blue or mu star plus blob or epsilon star. So that's it. We don't let that bother us more. The corresponding formula is available for the transformed model B here, but we can forget that quickly. And we can ask now, where on earth are we now? It is always advisable to ask that from time to time. In this picture, we are in Manipal, South India. Excellent performance 4 years ago. I am right now here in Viinikantie 11. If I started walking towards Mangalore, the route would be like this. It would take almost 2,000 hours, 8,000 kilometers. I would end up to Mangalore if I would use this map. Mangalore would be incorrect destination because Mangalore is not Manipal. Manipal is nearby, but they are not equal. Next section of my talk is number 6. And I'm dealing here with the coefficients of Y, yielding blues and blobs. We define the set Px star M in that way that B belongs to this set if B matrix satisfies this fundamental blue equation. With this notation, G star belongs to Px star M. That provides the blue for X star beta in the original model. W belongs to this script W set down here. If G is defined in this way, then that is one matrix belonging to this class Pxm. And B belonging to this class, that is a solution for this equation. It is unique if and only if the rank of xv, which is the rank of xvm, which is the rank of w, is n. Otherwise, the class general member of this class can be expressed in this form: G plus T Q W, where T is a matrix which is free to vary. And if rank W is precisely n, then there is precisely one member in this set of matrices. Under the transformed model T, CFY is blue for mu star if C satisfies this fundamental blue equation. Here is model matrix part. This is covariance matrix or transformed model, and here is the orthogonal complement of the design matrix in this transformed model. So C has to satisfy this, and then CFY provides a blue under the transformed model. And we use the notation C belongs to this class Px star T if C satisfies this fundamental equation. And what is of interest is the set of matrix products CF where C belongs to this particular class. And this class will be denoted in this way down here. This is any member from this class, but F here is just one single matrix. And this means that if D belongs to this class, then we apply this D for response Y, then the result is the blue for X star beta under the transformed model. Now Paxellari and Kala in 86 showed that if Fy is linearly sufficient for X star beta, then every multiplier CF of Y, where C belongs to this previously defined class, that provides the blue also under the original model M. This is using mathematical formulas or sets. That's this statement. And we can one more time say that using more words, every representation of the blue or mu star under the transformed model T is blue also under the model M. That means this kind of set inclusion. That was 86 by Paxellari and Kala. And next section, I can promise you this is the last one. And here we consider the vice versa problem. And what it means is that we consider two sets of multipliers for Y. This set provides the blues for X star beta in the original model. This provides this set the multipliers in the transformed model. We are interested in these two sets. And Paxellari and Kala actually, they showed that if Fy is linearly sufficient, then this set is a subset of these matrices. So that I have stated already earlier that this is indeed holding. And now the question is coming. When does the reverse relation hold? Here we have that the multipliers of Y in the transformed model, they provide the multipliers in the original model, but the vice versa relation was not solved thoroughly by Paxellari and Kala. The result appears to be on this slide. If we assume that Fy is linearly sufficient, then the equality of these sets holds precisely when this inclusion star holds. We were very pleased when we were able to confirm this result. It was not so easy. Here it is repeated what I just explained, so that if we have linear sufficiency and star holds, we need the star equation inclusion. Each representation of the blue or X beta star, X star beta under M is a representation of the blue under the transformed model and vice versa. And the same concerns also the blobs. So that's interesting. The same concerns the blobs. This is one symbolic way to express the situation. Blues for X star beta are the same in both models under that condition. Here is an interesting, at least, if not even nice, application. We take the partitioned linear model and then we take F is a transformation matrix we apply to this original model. We pre-multiply this model, full model, with M2, which is I minus PX2. what happens is we get rid of the second part here. This is now considered a nuisance parameter, beta 2. We get rid of it. We have reduced model, as it is often called. Response is M to Y, etc. The model matrix part is here, and beta 1 is the parameter covariance matrix is this. And if we do this, what happens is that, as I said, F is M2, and now X star. We have been earlier we have been playing with X star, and the parametric function has been X star beta. Now X star is F times X, and in this case it is M2X1 and 0 matrix here. This means that X star beta is that fellow here. This is the parametric function with what we are estimating if we do this transformation reduction. And then it happens, it appears that these two sets are identical. So this theorem now shows that in this particular case, very easily one can see that the condition which is required there, it is holding, and therefore these two sets which provide the multipliers when we are estimating this parametric function. If we estimate that under this model or under this model, the sets are identical. And this is, I'm repeating myself, which I seem to be doing from time to time. And here, in this condition, the blues of this parametric function, they are the same under original and in the transport model. And anyone who's been, okay, let's stop that sentence. Here it is said in another way, if beta 1 is estimable in a partitioned model, then the blues for beta 1 are the same in the original and in the transformed model. And this is nothing but the Frisch-Bohr-Lowell theorem, famous, very well-known theorem, but this is also something more general in the sense that this proves that the multipliers for Y providing the blues, the sets are identical under this particular condition. And here is a summary of what I was trying to tell. The aim of this talk has been to provide an easy to understand review of recent results that ordinary mortals can appreciate. And I think I made it. Namely, I was able to go through the second part of my presentation, and here is my last slide, and therefore I will now thank you for your forthcoming attention. Thank you very much.
Thank you very much, Simo, for a nice review of the linear sufficiency. I don't know so many other colleagues that can present 69 slides in 30 minutes. But, you are the master.
You're very generous in your compliments.
That's very good. So, is there any comments or questions for Simo? This is the bad thing with this distance conferences, online conferences, that is not so easy. It's much easier to just raise your hand and have a question or comments if you
everyone in the room looking for lunch.
Yeah, exactly. We will have our morning coffee here now. No, so if no more comments or questions, then I would like to close this session and say once again thanks for the conference and for the organization. And yeah, so see you later again. Thanks.
Okay. We'll go for lunch and you take breakfast.
Okay.
Good. Bye.
Raksha, over to you.
Thanks a lot, professors, for the wonderful lecture. I also thank Professor Singhal for chairing this session. Now let us have a lunch break. We will join after 2:10 IST.
my lecture, matrix volume and application. The volume of
Hello.
Good afternoon. Yogi, good afternoon.
Good afternoon.
So others have joined? Santosh and other?
Let me check. I mean,
Andres.
so you can see the list.
Yeah, I'll check.
Yeah.
Yeah, he joined.
Okay, okay.
Umashankar, you can bring them in. Andres as well as Santosh Singh. Umashankar.
Yes, sir, he's doing that.
Hello, good afternoon.
Good afternoon.
Good afternoon. So how is Dominic now?
Dominic is recovering. He contracted COVID some time ago, and well, his condition. Well, he was okay, but he suffered from high temperature and stuff like that. He spent this time at home. Unfortunately, currently in Poland, we have a lot of COVID cases. I'm myself at home isolation right now because last week I found out that I was tested positive for COVID, but my condition is very good. I don't feel bad, so it's okay. But I'm here at home right now, and you know, with all kids around, I hope they won't disturb our conference.
Right. So
yeah,
in fact,
we are missing him second time. For the second time, we are missing Dominic.
Oh, really?
Yeah. Last time he came up to Delhi and went back.
Oh, I didn't heard about that. But you know, that's unfortunate.
So I was very much interested, no, that whatever the work you are doing, no, that working with real big data, so that you will share with the participants, no, that so probably that you will be the one of the speaker, no, that who will be really working on big data sets.
Oh, that's good. Yeah, I'm very curious to hear other presenters as well. So.
Yeah, just search for Santosh Singh. Yeah, we will. Maybe we'll proceed. Maybe Singh will join us later.
Yeah, you can proceed.
At scheduled time, 2:10 we'll start. Hopefully he will join us later. Or he may be still having problem with the network?
No, it should not be. That he is in the university, so So it's not be a problem with the networking. So first that you can start with my talk and then Andres and then followed by Santosh Singh.
Yeah, Raksha will invite you with your team. Okay, then later you can just formally invite your colleagues, speakers, you being an organizer, and brief about them, and then later we can start the talk one by one. So first is yours, and second is Andres, and third is Santosh Singh. Am I right?
Yes, that's right.
Okay.
Welcome back, everyone, to the mini symposium on recent methodologies in big data analysis. Organizer of this session is Professor S.K. Niyogi from Indian Statistical Institute, Delhi. He is also one of the speakers in this mini symposium. Based on his research and teaching interest in applied statistic and matrix method, he has published several research facts on hidden Z matrices and the linear complementarity problem, completely mixed strategies for generalized bimatrix and switching controller stochastic game, etc. Today he will be talking on statistics and big data, a research paradigm shift. Another speaker of this session is Professor Andrzej Janus from University of Warsaw, Poland. He is an active and experienced researcher in the field of science related to data exploration, machine learning, and artificial intelligence. He participated in several R&D projects funded by NCBR related to such topics as semantic indexing of scientific publications, assessment of threats during fire and rescue operations performed by the State Fire Service, and active monitoring of safety conditions in underground coal mines. He is also co-founder of Knowledge Pit, an online platform where he organizes open data mining challenges aimed at solving complex real problems. Today he'll be talking about learning from video game logs, the human in the loop approach. We also have Professor Santosh Singh from Shivanadar University. He is also head of Big Data Analytics Center. He has been a member technical staff at Siemens Research and Corporate Technology, Bangalore. His area of interest is medical image analysis, image reconstruction, filter bank theory, computational photography, light field, and optimization technique. Today he is talking about trends in big data technology. I welcome all of you. I now request Professor S.K. Niyogi to take over. Over to you, sir.
Thanks, Raksha, and I thanks all the speakers in this session. We have 3 speakers in the session. The session will start with my talk, and then with Professor Andres, and followed by Professor Santosh Singh. And so I'll start my talk, and this talk is a recorded one. This is done in order to avoid if there is any break in the communication and all. So now, Uma Shankar, you can play the talk.
We are playing it in a minute, sir.
Professor Prasad, for giving me the opportunity for organizing this session. In fact, this is in continuation of my talk, which is delivered 3 years back for Sambodhi Research. The title of my talk, Statistics and Big Data, a Research Paradigm Shift. The advent of big data has opened up new avenues of research in statistics, computer science, mathematics, social science, and made it possible to answer questions that were previously unanswerable. In fact, that the big data is transforming the research environment. More and more data are being produced by an increasing number of electronic devices physically surround us and or the internet. And the large amount of data and the high frequency at which they are produced have resulted in the introduction of the term big data. Because of the fact that these data reflect many different aspects of our daily lives, and because of their abundance and availability, big data sources are very interesting from statistics point of view. Today, in sectors like social development, healthcare, education, energy, governance, etc., have more data than they can handle and recognize the potential for value. But the promise of big data is still has not been realized, according to the leading academic and business media sources. So in this talk, we aim to gather an understanding of the potential of big data. So in this talk, I'll try to answer the following questions. What are the efforts to use big data for creating sustainable impact in the Indian context? What are the various challenges and opportunities that big data presents in different fields? What are the potential of big data and analytics for achieving maximum and lasting impact? And what are the methodologies for analyzing big data? So let us understand the difference between small data and big data. Small data, so here sample size is small, and this fit into the conceptual structure of statistical, classical statistics. This is neat and clean. And what about big data? data sets whose size is beyond the ability of typical database software tools to capture, store, manage, and analyze. So let me elaborate further after this. So what are the potential opportunities? New statistics, more detailed statistics, more timely statistics, early indicators of any problem, quality improvement, response burden reduction, cost reduction, and higher efficiency, and there are many more. The 4 V's of big data is known to all of you: volume, velocity, variety, and veracity. Now, that the big data, so that we can relate to data science, and big data is a data whose scale, distribution, diversity, and or timeliness require the use of new technical architectures and analytics to enable insights that unlocks new sources of business value. And data science, in fact, is the principal means to discover and tap that potential. Data science provides ways to deal with and benefits from big data, to see patterns, to discover the relationship, to make sense of stunningly varied images and information. Now, data structures which are available, we can classify the following: that structured data contain a defined data type, format, and structure. So structured data is very rarely available in practice. Semi-structured data, so textual data files with discernible pattern that enables parsing, such as extensible markup language, XML, data files that are self-describing and defined and by an XML schema. And quasi-structured, this textual data with erratic data format that can be formatted with efforts, tools, and times. And for example, WebTil extends data that may contain inconsistencies in data values and formats. So therefore, it's a big challenge, no, that you cannot analyze the data as it is. So you have to convert quasi-structured data and semi-structured data into the data in structured form in order to do reasonable analysis. And this unstructured data, this data has no inherent structure, which may include text documents, PDFs, images, and videos. So in this case, that the problem is increased in many folds, and it is really challenging for us that how to convert unstructured data into a structured data. Now, if you look at inverted pyramid structure of quantitative data analysis, so we have raw, in fact, we'll use the term dirty data. So we need to do data cleaning and aggregation. And once you have cleaned and aggregated data, then we think about appropriate quantitative modelings, and we make use of these models for making predictions, and this we may use for the portfolio allocations and evaluation and various other purposes. Today's methodologies are different in terms of how data are collected. The intrusiveness of the procedures and the degree to which methodologies applies to situations, specific versus universally observable behavior, that these things have to be looked into. Now, when I talk about paradigm shift, this is in terms of not only methodologies for analyzing big data, but also that computational methodologies in the presence of big data. So therefore, that obvious question arises, how are big data supporting a research paradigm shift? So let's look at traditional research investigations that involves methods or procedures and techniques to describe and explain behavior. We make use of the tools like test of hypothesis, sample surveys, judgment task, design of experiments. So this is used to establish new truth and simulation. We may make use of forecasting methodology. So this is the traditional research investigations, but big data has caused the scientific community to examine or re-examine that all the methodology I mentioned just now. So for scientific research. Now, if you look at big data technologies and the corresponding fundamental research, so that have become a research focus in academia. So you will see that most of the universities, all the universities, that they have a department which deals with big data and then the computations related to big data. In fact, an emerging interdisciplinary discipline that called data science that has been gradually coming into place. So this takes the big data as a research object and aims at generalizing the extraction of knowledge from data. So it spans across many disciplines that includes information science, mathematics, social science, network science, system science, physiology, and economics. So this covers almost all the areas of the disciplines. And in order to work with the big data and drawing conclusions from the big data, you need to have domain knowledge from all the branches of science, which I mentioned just now. And computational methodologies, you need almost everything. You need probability theory, you need machine learning, you need statistical learning, computer programming, data engineering, pattern recognition, uncertainty modeling, data warehousing, high performance computing. So this is a small list. So this list we can add on further. So there are a large number of computational methodologies which we can make use for analyzing big data. So for example, big data predictive analysis has been applied to address societal issues that includes public health and economic development, and society can get enormous benefit from analyzing the huge data which we are generating every day. And note that hardly that maybe 20% only we are using it for analysis. So the remaining things have to be analyzed, and so we need to look into that. What are the methodologies you will do the analysis? What are the computational procedure you will adopt? So everything you should need to look into once again. Now, let me give you an example in healthcare. Ginsberg et al. Found that if the volume of queries submitted to Google with keywords like a flu symptom and flu treatment, and this kind of queries, if it is increased in a region, that then after a few weeks, the number of influenza patients to the emergency room of hospitals in the corresponding area will increase accordingly. So you can see that the kind of term is such that is directly related to something, that some infrastructure arrangement and so on. So therefore, that you can take many administrative decisions based on these facts, analyzing these facts. So with that discovery, they will be able to predict outbreaks of influenza and deploy countermeasures in advance. So that's the beauty of analyzing. If you analyze that search engine query data, so you can make use of that very effectively. Now, challenges of big data. Now, the emergence of big data has provided us unprecedented large-scale samples when dealing with computational problems. And although we now have to face far more complex data objects also, as I said, that data that you may have a mixture of image or PDF files or text data or numerical data. That analyzing a mixed data is the big challenge, and it's the big research objects. And so apart from that, the large scale samples, and so here that how to apply the sample survey methodology, existing sample survey methodology, that itself is a big challenge. So therefore, we need new approaches to analyze big data, and also that that in statistics we need various assumptions. Okay, and the new assumptions, new approaches will need to break away from assumptions made in traditional computations. Say, for example, that you need, for example, independent identical distributions of data and adequate sampling for genetic reliable statistics. So some of the assumptions you have to break away from such as some of the assumptions, and in order to deal with big data. So when solving problems involving big data, we'll need to re-examine and investigate its computability, computational complexity, and algorithms. So therefore, if the data size is very large, okay, so this computational complexity of the algorithms, which will naturally come into picture, and we need to re-examine that and investigate that. So this is also an open problem for future research. Now, when conducting empirical research with the data available, for example, now from online auctions or social network communications, mobile phone networks, gaming problems, search engines, which we have just mentioned, that or blogs of researchers need to be more open to exploration from the viewpoint for multiple disciplines. So you will see that this kind of different from the different platforms, that when you are capturing the data, so that will involve multiple disciplines or multiple area of domain knowledge, and that we have to look into more carefully. So therefore, extracting meaningful information from a large data set may require methodology and interdisciplinary flexibility. So note that the word interdisciplinary flexibility to create business intelligence for decision support from it. So therefore, you need a big team consisting of experts from all areas, the domain experts from all areas, in order to deal with analyzing the data and to take care of extracting meaningful information from the huge data set, which is a mixture of various things that, as I said, that it could be a mixture of PDF files, text data, numerical data, image data, and so this has to be looked very carefully. Now, at some point of time, when you are dealing with the small data, researchers are interested in small sample properties, and the corresponding methodologies are developed. Now, the data may no longer exhibit the small sample properties that many people in social science have been trained to work. So, as you know, that so many of us are trained in analyzing small data. So now that there is no problem with the data, that now it has become very large, and it has become highly unstructured, and so this is the big challenge for us, how to analyze such kind of data. And also note that user behaviors in social networks may be correlated, which require new methods to make sense of the causal relationships that are present. So, this has given many new research problems in various areas. In fact, that plenty of problems, no, that which require new methodology, and you need huge number of researchers to deal with with the problems of in data science and analyzing in an appropriate manner. Now, one question often arises, no, that there could be strategy for collection of data. Okay, and in today's date, that more frequent data collection is possible, and the real world often creates situation in which the researchers is able to take advantage of changing conditions. For example, the acceleration of online competitions, change in market demand changes. You can capture it very fast if there is a new service mechanism and so on, and iterative research design create new power. Now, how to overcome the bottleneck caused by big data in Indian context? So let us discuss that. Many practical problems are distributed and require protection of the input data. So the data may not be shareable. For example, in supply chain master planning, the participating companies need to exchange information about production cost and capacities. And this is a very sensitive data. And since it directly impacts the negotiation position. Now here, that nobody can share the data, but they can give the data in a common platform after some transformation, and then it can be analyzed, and then you can decode it later on or get the decisions there. So that gives rise to say privacy preserving linear programming. Okay, so there are several parties can jointly compute a function, for example LP, without disclosing anything except what can be inferred by a party's input and output. And in the theory, there's detailed theory available by Mangasariya. This offers an ideal solution to the conflict posed by these problems. Now, big data as a data source from official statistics. So this has become an important source, interesting source for official statistics, as it enables the potential production of speedy and considerable relevant of official figures as a relative low cost. A number of challenges have been identified that need to be addressed when starting to use big data for official statistics. Now, if you see various statistical institutes, they typically do not own big data sources. In fact, that when you teach the methodologies which involves big data, it is also a challenge for us, no, that we need big data sources, no, that in order to explain the methodology, and the institute doesn't have that. So a first challenge thus is to obtain access to the relevant resources, and access is not that easy. So this will imply agreement with data owners and data processors who have their own concerns regarding cost, confidentiality, and other issues. And even some cases that it is it is a paid one, that you have to pay an appropriate amount of fees in order to have access of those data sources. However, they might also benefit from cooperating with statistical agencies. So they will benefit the development of the new methodology or with their appropriate data. We can develop the appropriate methodologies. The terms and conditions have to be negotiated that are acceptable for both official statisticians and data providers. So both will mutually benefit. Now, regarding that privacy protection, which I just mentioned, of individuals is imperative, but familiar approaches do not always work when dealing with big data. So you need to develop new approaches. And moreover, when the legal situation is not clear, statisticians may have to fall back on ethical principles. And critical importance is the public perception of any use of big data, and this has a direct impact on trust in official statistics. Now, if you see that data sources and approaches, and we have survey questionnaires for administrative data sources, and while conducting a survey, we make use of sampling theory. And in fact, that we don't do 100%, we do a percentage of that, and which is based on sampling theory. So where does new big data fit in? So new methods may be needed, not based on sampling theory. So this we need to have a relook. So many big data are composed of event-driven observational data, which are not designed for traditional statistical analysis. They lack well-defined target population, data structures, and quality guarantees. So this makes it hard to apply statistical methods based on sampling theory. So therefore, that we need to again relook in these areas in order to develop appropriate methodology. For example, accessing selectivity issues is very challenging. Okay. Since an increasing number of big data sources are text-based and composed of images, so that gives us a real challenge for analyzing such data And so they need to extract information for these kind of data sources, and analyzing text-based data, that it is going on increasing. So you need such analysis more and more. So this calls for information on extraction method such as text mining and machine learning techniques that you may have to use, and which is not yet familiar to many statisticians or those statisticians which are dealing with official statistics. So extracting statistical meaning from big data source is not easy. How? That, for example, a tweet or a phone call of a car passing a detection loop all relate to a person, but how to interpret these signals is far from obvious. So let me elaborate this. For example, that interpretation of mobile phone data is hampered by several issues. So what are the issues? People may carry multiple phones or none. Children use phones registered to their parents, and phones may be switched off. Okay, so therefore, that analyzing this kind of data is not that obvious. For social media messages, I'll give some examples. Similar issues may arise when trying to identify characteristics of their authors. Remedies like deriving the gender and the age of Twitter users from the choice of the word, the kind of word they use in their message that may make it visible in order to identify the gender. So you need to think about the new methodology, and still a lot needs to be done. There are a few things that are available, but this is also an open area for research. So let me give you give an example of social media data. So here, that social media messages, those are written in Dutch and they're public, and data collection is systematically and instantly, and these are collected by the Dutch firm Costo, and some value is added by Costo on sentiment, and this is a paid subscription, and data set is more than 3.5 million messages covering June 2010 to till present, and there are 3 to 4 million messages added per day. So you can imagine that the size of the data, it is really huge, and so those when the sentiments can be analyzed for various platforms, whether Facebook, Twitter, blogs, LinkedIn, YouTube, etc., and year-wise, and you can see that how it is varying, that how the sentiment is varying over the years of particular issues. So this gives the development of daily, weekly, and monthly indicators of social media sentiment from June 2010 to November 2013, and you can see that in green and black respectively. And the development of consumer confidence is also shown for the identical period. And you can see that basic emotions in social media, some of the basic emotions are happy, excited, tender, scared, angry, or sad. Those basic emotions that you can figure out that during this period, that when they are happy, that how it is varying, that which period they are happy, which period they are not happy, and so on, sad or scared or tender. So this data are analyzed. So this are adapted from different studies. These slides are adapted from different studies in order to give appropriate examples. And you can see that sadness, how it is varying. And based on the average sentiment of public Dutch Facebook and Twitter messages. You can have this. I mean, so here that Indian data was not available, so I have to make use of some of the resources which are available in the internet. And now we look at overview of the issues, that what are the problems involved, that getting access to the data, privacy, confidentiality, and reputation. So we can summarize that the two main things. One is main bottlenecks, that one is getting access to the data. Second is privacy, confidentiality, and reputation. Now, third is the usability of the data. Whatever data you gather, how much it is usable. It may so happen that you use huge amount of data and perhaps that 50–60% are not usable. Or even if you want to make it usable, no, that you need to do lots of deworking in order to use the data. Okay. So therefore, that usability of the data is another important issue. You may have to get the meaning of the data, stability of the sources, reproducibility, etc. And then fourth point comes, that is methodological issues. You know, that selectivity, representativeness, and population is unknown, quality and validity. So that all those issues are coming into picture. And obviously you need that huge IT infrastructure and security. And you need, in order to handle this kind of complex data, you need knowledge and skills. And so that it will facilitate the transition from research to production. And there are statistic challenges ahead. So you can see that there are various issues involved to deal with the big data. And so we understand the difficulty, and there's, as I mentioned, that a lot of research work needs to be done in various areas. Now the question is that what is the future of big data? What are the challenges ahead? That what are the policies we should look into while collecting the big data or gathering the big data? But one thing is sure, that big data is here to stay, and it will go further bigger. Okay. So embracing big data and data science into data statistics is the only way forward. We need a research paradigm shift, so which will typically that address that the real problem which are faced by big data. I'll stop here. So if you have any questions, I'll be glad to answer. Thank you for your patience and attention. So any questions?
So, maybe I have a comment, if you allow. Thank you for this presentation. It was very interesting. You covered so many relevant topics in that talk. And I have to say that it's really well said, because my private experience dealing with big data, especially those questions related to data privacy and security, are very important, and you highlighted that. In many applications, you need to have consent from people to process their images and things like that. And from the legal perspective, it's very difficult to get those consents post factum. So that really restrains research in many areas. Even though you have the data, you have access to the data, you cannot process the data legally. So this is very, very interesting topic, how we can somehow avoid this. And for instance, first code the data somehow, blur faces automatically, and then process data, for instance. That's very, I think it's very, very important topic and open questions to data science community.
In particular for image data, it is really, really very difficult. No, that how you will transform the data and all. No, that's really different. I mean, it's difficult problem. It's to be addressed.
Yes, I think that also. And about finding good data sources, I think a very good thing are open data mining competitions. I don't know if you have heard of this trend, I would say, but many companies, many institutions open their data sets to public because they organize some kind of data exploration challenges or data mining competitions. Usually, you cannot really say that they provide big data, but sometimes this data that they provide is sufficiently big for interesting research. And that could be for academic community a very interesting data source because it supports reproducibility of the results, you know, because there are usually so automatic evaluation systems and many teams from around the world compete so they can compare their results and sometimes discuss it on the conferences. And this is beneficial both to the scientific community, I think, and for those companies that organize those data mining challenges as well. Because they get some interesting insights about their data, they get very
both
broad.
will benefit. Both will benefit.
Yeah. So I think this is a nice thing that people more and more often organize such a competitions. And last thing I wanted to comment or ask you about is the problem of availability of data labels. I will discuss that during my talk actually, but very often when dealing with big data, we have the data. We have like open data sets with social media tweets and things like that. And even in your talk, you showed such a data source. But I wonder how was those indicators of emotions, how they were computed for those big data sets, because I'm guessing that they were computed either using simple heuristics based on dictionaries, and you know those methods are efficient but not very accurate in practice.
You are right. I mean, there also needs a lot of things to be done.
Yeah. So because there are no real labels, like person who tweets does not add tags that I'm happy or I'm sad right now, right?
Right.
And in practice, someone can write I'm sad, and that means his emotion is that he is sad, but he can also write I am not sad, and typical text mining algorithm would only identify the word sad and associate sad emotion to it, where the person says that he's actually not sad at all. So this is those kinds of problems are very complex, and I wonder whether, in your experience, you find out any means to deal with it, like deal with this lack of data labels in practice.
So definitely that I mean I'll be glad to know such data sources. That the problem is with us, the data sources. Now, as you say, that there are various data sources available. So maybe that our students can be in touch also with you. That when we do such projects, and we will be glad to be associated while dealing with such projects. That to contributing the methodology and all. And so there are a large number of problems that are associated with big data, which needs to be addressed by the research community. And as you know, that there are a huge number of researchers are coming into this field and in the field of data science, and so we need still a lot more. Huge work needs to be done. In fact, this has given a total orientation of the statistics. You know that now it is not. It is we have to work together with the computer science people, statistics people, mathematics people, and economics people together in order to get a real benefit of it.
Yeah, I totally agree.
So we'll be really glad to be associated. That in touch. In fact, that I talked some of the people earlier also that about this.
Can I add one more thing to the challenges what Andres was talking about? When it comes to the sad happiness, it's not just sad and happiness. It also has to give an account of the level of sad and happiness, because certain people get sad very quickly. I mean, you say, oh, shut up. And the person is sad, person is depressed. And there are people who are very tough in a sense that they don't get upset or they don't get sad or happy so easily. So how to measure that effect of sadness and how it impacts the algorithms or how it impacts the result of it also is something which is very important. Probably. And initially, if I remember correctly, then it was the Google who has predicted on the flu shots. And all of a sudden, everybody got a panic and everybody started thinking, okay, I have a nose problem and I got the flu. And the drugs were out of control. And then based on that prediction, the drug company made too many drugs. I mean, it was too much of the supply in US. And that's how, so that also has to be taken care as what is the intensity of somebody saying, but it's a very subjective and I don't know, it's a very open challenge kind of a problem to figure it out. What is the extent of those emotions actually?
So we should motivate our students, no, that to work on this field, which will be really useful for the scientific community. In fact, for everybody. So if there are no other questions, we'll thank all the participants for carefully listening the talk. And now I will request Professor Andrews to present his talk.
Hello, everyone. My name is Andrzej Janusz, and it is my pleasure to be a part of the symposium on recent methodologies in big data analytics. The title of my presentation today is Learning from Video Game Logs, the Human-in-the-Loop Approach. Before I start, I wanted to tell you a bit about myself. So my background is in mathematics and computer science. I received my PhD degree in 2014 from the University of Warsaw. And since that time, I'm working as assistant professor at the Institute of Computer Science. I also work as a chief data scientist at QED software company. And I also founded a knowledge feed platform that we are using at QED Software to organize international data mining competitions. My plan for today is the following. So I will start by giving you some motivation behind our research in the field of active learning. I will explain what active learning is and when it is worth to try this approach in practice. I will also discuss the main issues that active learning is striving to solve. Then I will talk about our recent project at QED Software. This is a still ongoing project, and I will use it as a demonstration how active learning can be applied in practice. I will finish by summing up my presentation. So, we can say that we are living in a world of big data. In many applications, it's quite easy to generate a lot of data. So you can think of sensor networks or Internet of Things, or you can think about some process logs or sensors used in predictive maintenance tasks, social media or video streams. They all generate a lot of data. One special application field that I will be talking today about is video games, because they also can be seen as a kind of processes, games I mean, and they can generate a lot of data on the way. But in all those applications fields, even though the generation of the data is easy, the acquisition of good quality labels for that data is not. And what are the problems there? So when our aim is to develop a prediction model for that could automatically label the data, well, we face a kind of a chicken and egg problem. So we want to have a model that can automatically label the data, but to train this model, we first need labeled data. Otherwise, we cannot do that, right? So if we don't have enough data, we cannot train. Moreover, in many application fields, even if we have some labels for historical data, they may not be valid anymore, because if the data changes in time, we can have problems with concept drifts or data distribution shifts. And for those reasons, we need, in order to keep our prediction model valid, we need to constantly update that model. And to do that, we need labels for new incoming data, not only the historical ones. However, the manual labeling of data can be very difficult because it requires a lot of time from experts. Sometimes it's not that severe, because in some cases we can outsource the data labeling to community, and it's sometimes called crowdsourcing of data labeling. But in many practical applications, some expert knowledge is really required to label the data. You can think of medical applications or applications in the cybersecurity domain. They all require some very specialized knowledge in order to be able to label data correctly. And it's not easy. You can say that, well, if you want to have labeled data, you can sample the data randomly and give those samples to experts. However, it's not that easy, especially when distribution of the labels is not uniform. When the distribution of the labels is imbalanced, then we do not want to show to experts very similar examples or only examples from the majority class, because it will not be efficient. we want to optimize the amount of time they need to sacrifice for this manual data labeling. And moreover, in those difficult cases when the labeling of data requires some specific type of knowledge, the labels assigned by experts can be inconsistent. So if the same sample is shown to a few different experts, they can label it in a different way. And that's also problematic, and we have to cope with that problem somehow. So the answer to all those indicated issues could be active learning. There is no best definition what the active learning really is, but most researchers agree that active learning is a subfield of machine learning in which the learner can iteratively query the oracle and ask her to label some small sample, some limited samples of data cases. And the learner can use this information to update itself, so update its state of knowledge, and then repeat this process many times with each new sample of data increasing its quality. So you can imagine this as a kind of a cycle, sometimes called the active learning cycle. So you start with a machine learning model, and you have a potentially very large pool of unlabeled data. You can easily make predictions about this unlabeled pool of data. And based on those predictions, you can measure how uncertain or the model is when making predictions for individual data instances. And you try to select those instances which bears the most information. So those samples for which the knowledge about true data labels would bring the biggest benefit to the model. When you have selected those samples, you show it to the oracle. So the oracle usually is represented by some panel of human annotators or experts. And those humans annotate the data manually. And then you add those labeled data to the labeled data pool, which is much smaller, and retrain your model. And you repeat this cycle many times, right? So you can even repeat it indefinitely a number of times because you want to use it to adapt to new data that is coming to you. So in each iteration, the pool of unlabeled data samples can increase, for instance. So the questions that has to be answered here is how we can select those samples that can benefit our models the most. And in active learning literature, you can find many heuristic approaches to this problem. The most commonly used technique is called uncertainty sampling. In this approach, you have a predefined function for measuring how uncertain a given model was about the predictions for a particular object in this unlabeled data pool. So for each instance, you get the distribution of class probabilities or label probabilities from the model, and based on this distribution, you compute this uncertainty. And there are many different uncertainty measures that can be used here. Very often, simple entropy is used, entropy of prediction is used. So in this case, you are trying to select samples for which the prediction entropy is the highest, but very often maximum margin method is used for which in which you are considering only the two labels with the highest probability, and you try to select those cases for which the difference between the probability of the most probable label and the second most probable label is the lowest. And another approach, a very interesting approach to selecting samples for labeling is called expected model change approach. And it can be applied to any prediction model that is trained using stochastic gradient descent method. In this approach, you have some loss function, which is defined, predefined, and for each sample in this unlabeled data pool, you estimate the expected gradient of the sample if we knew the correct label for it. So you take the expected values under assumption with from the module of the gradient, and you select samples for which it is highest. This method is very interesting and it can work very nicely in practice. However, it has a limited use in the context of big data because unlike in this uncertainty sampling, you not only require to create predictions for each of the instance from this large unlabeled data pool, but you also have to compute as many gradients of the loss function as there are different labels. So it is definitely a less computationally effective method. The third method I wanted to mention here is called expected error reduction, but I'm only mentioning it because it can work in some scenarios when this unlabeled data pool is not very big. For big data, it doesn't have any practical use. However, when this set of unlabeled samples is not big, what you can do is you can compute the expected value of error reduction if we knew the correct label for that sample. So you assume that for each different label and each different unlabeled data instance, you assume that this instance has this particular label. You add it temporarily to your training set, and you create the model and you estimate its error rate, and you select samples for which this error rate is the smallest in comparison to the error rate without using this additional case. So as I said, this is very computationally heavy method, and it doesn't have any practical use when we face big data. So in our project in QED software, we decided to approach this problem of selecting samples for labeling in a slightly different, from a slightly different angle. We noticed in our research that it is very important to learn from typical examples for our data. So we don't want to learn from out of the distribution samples because they can actually do more harm to the model than they can do good, even if we knew their correct labels. So we want to take the representativeness into consideration. We also noticed that we are also trying to be focused on the work on experts. So it is really important for us to minimize their effort. For this reason, we cannot allow experts to waste their time. And if we try to select a single data instance in each iteration of active learning cycle, well, then if the expert would label this instance, then the group of experts would actually have to wait until we add it to a training set, recreate or update our prediction model, then select another sample for them. And that could take some time. And because of that, we don't want to do it in this way. We rather want to select a whole batch of samples in each iteration of active learning cycle. However, we don't want those samples to be very similar to each other because that wouldn't benefit the prediction model. So we need to consider the batch diversity. In the end, we decided to use the following formula in our system. It is a combination of uncertainty sampling, which is this first term in this formula. This phi function can be any uncertainty function that we can come up with. Then we have this second term, which represents the representativeness of samples. So we want to estimate how similar is a given instance to other instances from this unlabeled data set. And of course, in practice, if this set is very large, we don't want to compute all cross similarities in that set. In such cases, we rather estimate this representativeness by a different approach, for instance, using something by analogy to k-nearest neighbors algorithm, and we considered only similarities to the k most similar instances from this unlabeled data set. And the third term in our formula is related to this batch diversity. So when we consider a new instance and we want to check whether it's worth to be labeled, we compute dissimilarities or distances to all other previously selected instances in the batch. So in this way, we make sure that in every batch, the set of selected instances will be as diverse as possible. Another problems that we are trying to solve in our labeling the loop system is the problem with conflicts among the experts. So when we have difficult problems, as I said, the expert may assign different labels to the same cases. And well, there can be several different strategies in which we can resolve such conflicts. The simplest one is just to use majority voting. However, for the majority voting to work, each sample would have to be labeled by at least 3 experts. And well, that's quite a lot because on the other hand, we might have better ground truths for our training samples, but on the other hand, if we shown only one, given sample to only one expert, then we could label 3 times more data during the same time. So to cope with this problem, we also approach this issue differently. We model the expert labelings as mixture of Bernoulli's distributions. So we consider conditional distribution of expert labels, and we model each expert by 2 parameters for each different label type. we consider their true positive rate and true negative rate. So the probability that if expert assigns a given label to instance, the instance really should have this label, and the probability that if expert does not assign a given label to the given instance, the instance shouldn't really have that label. And in our algorithm, we feed those parameters of Bernoulli distribution using expectation maximization algorithm. And in the end, well, that allows us to create some very interesting schemas or heuristic in which how we assign instances to particular experts. For instance, we can try to assign given instance to an expert which is the most probable that he can correctly label the given instance. All we have to do that is to consider the probabilities issued by our prediction models and those parameters of our experts, and we can compute for each expert how likely given expert is to correctly classify a given instance. And of course, if we want to implement the voting procedure, then we can use those parameters as weights for the votes of experts. And that also can make this whole process more efficient, because now we can vote between two experts that assign different labels to the same samples, but we can choose the better label by considering those parameters that we estimated. All right, so now I wanted to describe this case study that we conducted in the field of video game data analytics. So we conducted this research for a video game called Tactical Troops Anthracite Shift. This game was developed by our own game developing studio. It is a turn-based tactical game. And what's unique about it is that AI for computer opponents for this game was created using our own Grail technology that facilitates creation of very advanced AI opponents in video games. It's very interesting game, very fun to play. So if you have some free time, I can recommend it to you. You can find out more about this game on this website, or you can find it directly on the Steam platform using this link below. So what we wanted to learn for this game was how to automatically recognize situation during the game in which something very significant happened that influenced the game outcome. So we call such situation game changers because of their outcome, because they're influenced on the game outcome. So if you think about it, finding game changers in any game, it's not an easy task, and not every player can easily do that, can easily recognize which particular plays or game moves were that significant. And there are many factors which can influence whether the given action or given turn, in our case, contain a game changer or not. In fact, in most of games, there are really no game changers at all, because if two players play the game and one is significantly better than other, then Well, it wins the game because of the tactics that he used and his skills. And there often are no breakthrough moments in such games. However, from time to time, it happens that when two players play the game, some specific events or very smart move allows one player to win the game. And those situations are what interest us the most. So to be able to do that, to learn it, we gathered a lot of data. We actually acquired about 400,000 game turns represented by a very diverse types of informations. Those turns came from real games played by testers and AI bots during the testing period of the game, so before the game was launched on Steam platform. Well, it contained a lot of diverse types of informations about the game states because it contains information about maps. This information was in form of bitmap masks with many different layers representing different types of objects on the maps. There were, of course, representations of units in game logs. So there were textual game logs, which had information about unit types and statistics of those units, such as HP or action points. There was information about weapons used by those units and their statistics, and there were also gadgets and their statistics. So the representation of a single turn in this game was very, very complex. And it was kind of a research issue to come up with a representation that would allow models to learn which turns contain those game changers. We decided to approach this problem of constructing the model and applying active learning approach for it in a specific way. We divided it into two phases. I haven't mentioned that before, but in active learning, the first cycle of active learning is very different than all other cycles because, well, I told you that we are using predictions of models to select samples for labeling, but in the first cycle, there is no model because there are no labeled data points which we can use to train it. Right? So the first iteration is usually performed differently. And it can be performed by first sampling the data at random. However, this is not very effective way because, as I said, in our case, those games changers are quite rare. We roughly estimate that only one in 100, there is one turn containing game changer in 100 turns. So about 1% of data we expect to be game changers. And if we sample and select the first batch at random, then we either would have to make it very large, or we would risk that there are no game changers in the first sample, and that wouldn't allow us to train this zero model in a reasonable way. It would be useless, and all the results that we obtain would be questionable. So we took a different approach. We started by constructing a prediction model to a slightly different task. Instead of identifying game changers, we trained a model to recognize which of the players is going to win a game. considering the current situation, considering the current game state. So the model predicted win probabilities for each of the two players. Well, we reasoned that if we take a turn and we take the situation at the beginning of the turn, and we take the situation after the end of the turn, and those probabilities, those win probabilities are significantly different, then it is likely that something significant happened during that turn. So it is likely that this turn contains a game changer. So we used this observation to create the zero model, and we tried to balance the initial sample for labeling with the cases that we thought are likely to contain game changers and those which are not likely to contain game changers. Then, well, to create this first model, well, we used deep neural networks. So those different data modalities, such as the bitmaps with the masks for each of the maps, and this kind of spatial data, like unit locations, could be processed using convolutional layers. Output from those layers was concatenated to trainable embeddings that we used for categorical data and concatenated with standardized numerical values. So it was a quite complex architecture, but it allowed us to create internal data representation of each turn. And in the model for detecting game changers, we used the same representation that was trained on this supervised task of predicting game winners. We simply changed the input of the model. So instead of considering only one turn, we considered the beginning and the end of the turn. So two game states were on the input to our model. Then we have this trainable dense layer in the model, which was actually updated during the training process, because this representation of data was fixed. And then the output from the dense layers was just probabilities whether a turn contains a game changer or not. So it was simple binary classification problem for us. But thanks to this idea, we could use the transfer learning to start learning process effectively. We also investigated different approaches to creating this first model, the supervised model for detecting winners in the game. We actually organized an international data mining competition, which was a part of IEEE Big Data Cup this year. What was interesting, because this competition ended in October, what was interesting is that all top teams were using a different approach to this problem. They were actually manually performing feature engineering and then combining this with gradient boosted decision trees to obtain the predictions who is going to win. And this approach turned out to be more effective than our baseline model based on neural networks. If you are interested in this topic, I cordially invite you to our special session devoted to this problem, which is being organized at IEEE Big Data Conference. And this special session will be held on this Friday. So if you are interested, I cordially invite you to join it. To sum up my talk, I hope I convinced you that active learning is a very interesting approach, and it can be used to extract real value from a large volumes of unlabeled data. And I also tried to advertise a little our own system implementing active learning, which is called Labeled in the Loop. I haven't talked about a lot of the functionalities offered by that system because I didn't have time. However, if you are interested, just contact me and I'll be happy to tell you more about it. Thank you very much for your attention. I will be happy to answer any of your questions, or you can send them to my email address. Thank you.
So thank you, Professor Andres, for a nice talk. And so I also work in game theory, stochastic games. So I'd like to see some of your papers. So whether you can send me some of your papers so that I can have a look at it.
Papers about the game itself.
Publications. I'm talking about publications.
Yeah, I understand, but what sort of topics are you interested in? Are you interested more about the game development and AI for those games, or rather machine learning approaches that we use to create AI bots?
What are the machine learning approaches?
About active learning.
Right.
Okay, so yeah, of course, I will. I can send you papers.
So many things will be, some references will be available in your website also, probably.
Of course, I'll be happy to send it to you.
Okay. So perhaps I should thank you that you quickly agreed, and in spite of COVID, that you are present here. So that itself is great. That COVID cannot stop anything.
Yeah, well, I was vaccinated, and thankfully, I think due to this fact, my condition is very good.
So in some conference, I would like you to meet in person. So probably that when we have some conference at Delhi, I can invite both of you.
That would be great. Thank you so much. I'm sorry because my son is bothering me right now. I'm trying to. Yeah, I'm fine.
Okay.
Because I'm from home.
I understand.
It's a lot of going on around me right now. I'm sorry, but you were talking about the conference in Delhi.
So any conference you organize, so we'll be glad that if you participate.
Oh, thank you so much. I really appreciate it.
So that we can have a more one-to-one interaction.
That would be great. I mean, the online conferences are nice, but it's the most interesting, and you can learn the most if you can personally meet and talk. That's definitely the better way of collaborating.
Please accept thanks from my end too.
So right, Professor Prasad, so I cannot see you actually.
You can't see me? But maybe.
So you have to keep your video on. Okay. So
yeah, it's off. Probably they did not put me in.
So in fact, we missed Dominic twice, but we should not miss thrice now. So whenever the next conference will be organized, I would like you to be there. Both of you.
Thank you.
Okay. So thank you very much. So now our next speaker will be Professor Santosh Singh. So can I see?
Yeah, I'm here.
You are here?
Yeah.
Professor Santosh,
I'm here. I'm here. So
So only thing is that if that after the presentation, if any questions are there, they can write back to him. No, that
yes,
so he
sure.
has some urgent work.
Yeah.
So should we play his videos? Okay. So you have anything to say? I mean.
Well, yes, I mean, I think it was interesting to hear both the talks, and I think mine is very brief overview, and it comes to, I mean, because I have to leave, I have a meeting with the Pro-Chancellor, which I cannot, unfortunately, avoid. The image data, and one thing which I just wanted to share, that it is not always necessary that we need to have the data in hand, because so much of data which is available on the web, I have used it in medical imaging case. So I did one problem which was classification of TB versus lung cancer. So I was not having, because the biggest challenge when it comes to the medical imaging, the problem is that you need just a real expert to identify and do the tagging and annotation of it, and which is again a big challenge, because going to the medical person, he says, oh, I'm not going to spend so much of time in tagging your data. So what I did is, it was an IBM project which I did it, is that I have some annotated data. Based on that, I collected the features, and then I put those features in such a way that it will acquire the images from the web, the CT, the X-ray images of lungs on the web, and then try to find out how to categorize and which category that image will fall. So it was done as a kind of a semi-supervised learning, and their automatic tagging based on the information which we had, and it was kind of a, I would not say it's a great success, but it was to larger extent it was a success. So image data, yes, it's a challenge, but one has to go through the computer vision kind of techniques, and there are a lot of things which can be used. Probably I have not seen much of the people using those kinds of techniques with the image data.
So most of the classical statistical technique may not fit.
They will not fit. Computer vision techniques will fit very well, and we need to change it slightly, in a sense that the computer vision people, they are not looking from the big data point of view. They are just looking image as an image or video as a video and trying to extract the features. How can we combine those two things together? That will probably is a much more useful and helpful thing. So that's what I just wanted to share, because probably I thought that I'll share it in the last, but unfortunately I have to go. So now.
No, thank you very much. I mean, so they can play the video that.
Yeah, 1 minute. Let me offer my thanks to him, please.
Thanks. Thank you very much. Thanks.
So if there are any questions, perhaps I'll answer on your behalf.
Yes, sir, sure. Thank you. Thank you very much. Thanks.
Professor Niyogi, I have one more word. After this session, Professor Lahiri may come in, and in such case, I'll request him to give a live talk, and please, you be the chairperson. Okay?
Who?
Lahiri.
So who will be the chairperson, you are saying?
Yeah, I'm requesting you to be the chairperson.
No, don't make me the chairperson. I have another job to do.
Okay. If you are busy.
So like him, no, that I have another job actually.
Oh, is it? Okay.
Okay.
Please carry on. I myself chair that.
Thank you very much.
Okay.
Thanks. Thanks, and yeah.
Thanks a lot.
Thanks.
Good afternoon, everyone. Here I'm Santosh from Shivnadar University, and today I will be talking about very briefly and giving a brief overview about trends in big data technology. What a strange times we are living in. Never thought that the modern song composition style will be adopted in academic conferences and workshops as well. Yeah, unfortunately, maybe most of the academicians don't like this way of organization, but because of this pandemic, what can we say? I mean, as French will say, c'est la vie. So that's life. So that's the way it is. Never thought of having such a kind of a way that I just will record and no audience and no direct communication with the audience. Anyway, So let's start. So here, before starting trends in big data technologies, I would like to give a clear picture about what is big data versus data science. As Professor Niyogi and probably others would have talked about this as well. And here there are 2 bullet points in talking about what is data science and what is big data. But I would like to give an example, real life example, where it makes it clear why we need to address these 2 issues separately and how they are linked, but at the same time they have to have a clear understanding of that only the big data and technologies are not going to play a role independently. So I'm sure everybody knows about what the e-commerce is. We have shops, e-shops like Amazon, Flipkart, and all these kinds of places where we can go. We can buy things. We can browse. We can look and all sorts of things. But from the e-commerce website point of view or a company point of view, they have a very big challenge as they cannot stop or they cannot categorize the people who are looking into or who are trying to access their website, because for them everyone is a customer and they don't want to annoy the customers by blocking certain group of people or taking too much of time to figure it out whether they are a real customer or a spammer, because there are spammers who would like to jam their site by just sending so many requests all at once, kind of in all at once, so that it becomes a problem for those e-commerce sites. So they have to on runtime they have to find out a request which is getting into their website or into their servers is a real customer or it's a spammer. So you can think of this is a very classical example of a big data problem where the technologies, where the algorithms and everybody has to work on it and sit and to find out in real time. When I say real time, in microseconds, they have to in a fly they have to find out whether the the request coming is a real customer or it's a spammer. So you can think of that how to handle that big data. There has to be a technology for that. How to address and do a classification where the whether it's a spammer or it's a real customer. So you can think of a mix of data science and big data technologies have to work together, but have a clear boundary and clear distinction within themselves, not to mix with the technology and not to mix with the algorithms and all sorts of things. And you can think of in this problem, you can think of that what kind of a lightweight algorithm has to which is going to work on in fraction of seconds. So that's what I just thought that okay, let me have at least one slide about big data versus data science. Now moving to the next slide. Here it's a very classical what you call is the a picture which is representing that how things are moving and what is the current scenario, how the data science or machine learning or data analytics or big data technologies are being talked in the everywhere. It's basically a fancy to talk about it, but a lot of people don't understand that how much of maths, statistics, and computer science is being used to solve these kinds of problems. So whenever we are talking about big data technologies, I would like to have just a quick word that it sounds very fancy, but it requires a lot of rigor in terms of mathematics and in terms of understanding of computer science and probability and statistics and all that kind of theory. Theory is very important. Otherwise, one aspect of it is not going to solve the problem. Then let's start with the big data. So here I have shown four major events which took in as a history of modern big data, where we are right now. They are the major role players as the foundation of big data started mainly with the Hollerith tabulating machine, which was created somewhere in 1980s by a young man named as Herman Hollerith. His invention was based on the punch cards designed for controlling the patterns woven by mechanical looms. This machine reduced 10 years of labor work into 3 months of labor. A huge reduction in time, which is a huge reduction in time. The motivation was based on dealing with the US Census Bureau in 1880s, because at that time US government was not sure how, if we collect the data, how we are going to process it, how we are going to get the information in a reasonable amount of time. So this machine was the part of dealing with that amount of data. Even you can think of dealing with that amount of data as still is a huge effort. That's how it started. Early, one can say the modern. That's what you will find in literature, and that's what I also believe in it. That STM was the thing which started the journey of the modern big data. What we are looking at in the current world or in the current scenario. So Pritz storing machine, that's the second thing, which was based on the magnetic tape designed by Fritz in 1927. He devised a method for adhering metal strip to cigarette papers to keep a smoker's lips from being strained by the rolling paper available at that time, and decided he could use this technique to create a magnetic strip, which could then be used to replace wire recording technology. After experiments with a variety of materials, he settled on a very thin paper, stripped with the iron oxide powder and coated with the lacquer. That's how this magnetic storing machine was designed, and it also plays a vital role in our modern computer science methods being used, and the programming and all sorts of things. The third picture is of Colossus. So during World War II, to be exact, in 1943, the British, desperate to crack Nazi codes, invented a machine that scanned for patterns in messages intercepted from Germans. The machine was called as a Colossus. It was the first data processor which scanned 5,000 characters in a second, reducing the workload from weeks to merely hours. And so you can think of how everybody was working on reducing the time. And it was what time we are talking about. One can, without any surprises, one can, or without any much of a calculation, one can think of that how these machines really reduce the processing time. So here we are talking about weeks and changing it to the hour in few hours. The fourth one is, I don't need to talk much about it. We all know about this person. The fourth picture is about the person who laid the foundation for computer architecture. John Newman in 1945 published a paper popularly known as EDVAC, Electronic Discrete Variable Automatic Computers. That has probably changed everything, and from there, what we have the start of personal computers and those kinds of things started. As also popularly known and being taught, I'm not too sure about it, that the US established under the President Truman in 1952, the National Security Agency. And because of these major 4 events happened during that period of time, he thought of establishing the National Security Agency. And that's how NSA started. That's popularly as a belief, I would say. Now the other thing comes as the ARPANET, where this is what Advanced Research Project Agency Network was the first packet switched network with distributed control and one of the first networks to implement the TCP/IP protocol suites. So you can think that initially they started working on the machines, then it comes to they started with the concept of the network, and that's how the whole journey started. And the big data, what we see, again, I will say what we see is of the reasons of these efforts which have been made in the past. In the second picture, in 1965, the US government, this picture doesn't need any caption, the US government plans the world's first data center to store 742 million tax returns and 175 million sets of fingerprints on the magnetic tape. It was this whole concept, this whole idea, and this whole effort got got a big problem because of people thinking that it can have it can steal their identity or whatnot. So I think that's what I read about it, that it was probably stopped in between and was not gone far ahead. But anyway, in 1965, the government plans to build up a data center to store that amount of data. So you can start thinking, again, how the movement started. Then came the personal computers. I'm not sure the current generation, how much they have really experienced those kinds of big machines. Of course, I have not even seen these machines other than in the museums or with somebody who had that as a souvenir or as a old memory in their house. Otherwise, the bulky computers now came to computers in our pockets. And the fourth is again a very popular person who was the inventor of World Wide Web, Tim Berners-Lee, and because of his efforts, what we have is we can know. No wonders, nobody has to say much about it. We all know what that whatever the advancement it is, because one of the reasons because of him as well. Tim. Now let's talk about the use of big data. Here I have just given very few snippets, or I would say very few use cases where the big data is being used. Now, I think everywhere the concept of big data is being used in one or the other way. People are working on it. They are trying to find out how they can enhance the potential of their businesses, how they can enhance the accuracy, how can enhance the predictiveness, all sorts of things they are using. They are working and using the concept of the big data. Healthcare to map disease outbreaks and test alternative treatments. NASA uses big data to explore the universe. Music industry replaces intuition with big data studies. And it's not only the music industry, it's everywhere it's being used. Utilities use big data to study customer behavior and avoid blackouts. Nike uses health monitoring variables to track customers and provide feedback on their health. Big data is being used by cybersecurity to stop cybercrimes. If one start talking about the uses, then probably it will be a day's time. It will take one day at least to talk about those uses of the big data. So as you can see, the domain of big data technologies or the big data is becoming vast and wide and wide and wide. it is majorly being divided into two different categories. One is the operational big data technologies. The other one is the analytical big data technologies. As the name suggests, operational big data technologies, which indicates the volume of data generated every day, such as online transactions, social media, or any information from a particular company used for analysis by software based on big data technologies. Few cases of operational big data technologies include information on MNC management, Amazon, Flipkart, Walmart, online ticketing for movies, flight, railways, on and on and on. Those kinds of usages. Whereas in case of analytical big data technologies, the concern is the real analysis of big data, which is essential to business decisions. For example, stock marketing, weather forecasting, time series, and medical records medical record analysis, essentially dealing with the development of algorithms and proper use cases in different domains. Now, from here, you can think again, relate the same thing with the which I was talking about, the big data versus data science. So you can have a clear picture about just an idea about how things are moving and how people are also understanding that what is technology and what is data science, how they are being used, and it's on those bases, they are trying to differentiate and make it clear distinctions where they are, what is going on. We'll just start with the top 5 big data technologies. As you can see, Hadoop ecosystem, artificial intelligence, NoSQL database, Python and R programming, data lakes. These are the popularly used data technologies. Under each of them, there are different categories, the modifications, newer versions with either the same name or with a different name coming up, or different group of people working on it. And as you know that initially they have been established by the research has been done, and the systems have been made by mostly starting with the researchers, and then slowly people in the industry, they started picking it up. So when we talk about these technologies, the names what we are talking about, they are not just new names. It is more of how they have been started and how big impact they made afterwards. That's how one can think of it. So Hadoop ecosystem, as we all know, Hadoop framework was developed to store and process data with a simple programming model in a distributed data processing environment. The data present on different high-speed and low-expense machines can be stored and analyzed. Enterprises have widely adopted after when the Google made the system, and Yahoo actually is the one who has really built up on this Hadoop and MapReduce ecosystem. So enterprises later on, everybody, I just remember being working in Siemens and how Hadoop and MapReduce was coming, and we were using it, and we were really having a fancy to think about it, that wow, what a technology and what a thing which is very so simple and is so effective. So it was now enterprises have widely adopted it as a big data technology for their data warehouses need in the current years. There have been advances to Hadoop ecosystem in different forms, as I said, but it's very much in use and accepted as a distributed technology. One very big is the advancement was after Hadoop MapReduce. It was Apache Spark, which was there. So it has Hadoop MapReduce has. As we know that every technology comes with some certain challenges as well, and it's not perfect. So that's how the new version, either in the same setup or in a different setup, is being proposed and is being used by or developed by the group of people. artificial intelligence. Again, it is not a new topic to talk about. It has been there. This topic and this concept has been there for a very long time, but now it is being used because of the latest technologies, the advancements in the hardware and the processing time. It is becoming very feasible and viable to use those concepts of artificial intelligence with the use of the big data and in terms of big data. Sorry, in terms of big data to go ahead with that, for example, Apple Siri to self-driving cars, all the kinds of these technologies, they use the concepts from the artificial intelligence as a multi and interdisciplinary branch of science. It takes into account a number of approaches, such as increased machine learning and deep learning, to make a remarkable shift in the most tech industries. Artificial intelligence is revolutionizing the existing big data technologies in a big way, where they are moving when it comes to the automation. The concepts of or the tools developed in the artificial intelligence are being used in a big way. So really changing the mode of usage of the big data technologies. It's a big game changer. Then comes as the NoSQL database. I'm sure everybody understands about the IWMS and the SQL, MySQL, and the structured data. Boeing was one of the, and still I think they use the concepts. They are working on a huge big data, but fortunately for them, all the data is the for their own, from the company point of view, is their own structured data, and they go ahead with that kind of a data setup. It's one of the biggest in industry for RDBMS. But as we know, in other industries as well as in other applications and domains, we cannot assume or we cannot talk about or think about the data to be structured. So there has to be a way to deal with it. So NoSQL database includes a wide variety of different big data technologies in database, which are developed to design modern application. It shows non-relational data, providing a method for data acquisition and recovery. They are used in web and big data analytics in real time. It stores unstructured data and offers faster performance and flexibility while addressing various data types, for example, MongoDB, Redis, Cassandra, just to name a few. Such data systems provide design integrity, easier horizontal scaling, and control over opportunities in a range of devices. It uses data structures that are different from those concerning databases by default. So you can see that how the importance of NoSQL database, where the data is coming from different types. It's not at all structured. It is not of one type of data. It's a voice, it's an image, it's a text. It's all kinds of data we are talking, and how to deal with that kind of a data is a big challenge. And this unstructured data and NoSQL databases, they are doing a fantastic job in taking care of that kind of data which we are talking about nowadays. When it comes to Python and R programming, I think not much needs to be explained as how R and Python programming took place in the advancement of big data technologies. They are being widely used for statistical computing and visualization. I think if you just look, or if you just see that the ladders of development in big data technologies, visualization is still one of the very niche area, and it's I would say, very much of underdeveloped. It's still a lot of work has to be done in visualization. It seems to be that people or the younger people who are in the universities or in they're doing some courses, they don't realize that how important is the visualization. And it's a big problem. It's a big problem because the world is a 3D world, and at the maximum we can visualize or we can very easily manipulate when it comes to the three-dimensional data. But when it comes to the multi-dimensional, which is the case in the big data technologies or in the big data, it becomes very, very huge problem, as well as when we are dealing with the amount of data. The kind of networks we are trying to build up. In that, the visualization becomes a huge problem as how to visualize, how to have a picture about what is going with the concepts of the big data in terms of how they are networked with each other, the dimensionality, and all sorts of things. So the visualization is in many senses is not as well developed as it should be. Then comes the the fifth one is the data lakes, which means a consolidated repository for storage of all data formats at all levels in terms of structured and unstructured data. Data can be saved during data accumulations as is without being transformed and structured data into structured data. It enables performing numerous types of data analysis from dashboard and data visualization to big data transformation in real time for better business interferences. The trend is that those businesses who have used data lakes stay ahead in game because it's a very big kind of a platform where all sorts of things can be done and performed with much of ease and not worrying about or not worrying about the integration. So the trend is that those businesses who uses data lakes stay ahead in the game from their competitors and carry out new analytics. Such as machine learning through new log file sources, data from social media, and click streaming, and lots of other types of things. So these are the big data technologies, top 5 big data technologies, which have impacted, which are people concentrating. They are working on it. Also, there are challenges to take care of the real world problems. So people are making an advancements in these technologies. These are, I mean, one can say that these are really the 5 big data top 5 big data technologies, which are making the maximum impact in this subject, and also maximum impact to the industry. Here comes is the emerging big data technologies, which are really. I would say it's those top 5 which we have talked, and now what we are talking about emerging big data technologies, they go hand to hand with each other. It's not that they are replacing. These emerging big data technologies are not a replacement of what I have just talked in the previous slides. It's just they go in one or the other way. They have just go hand in hand together. But as the newer concepts also keep coming up, and you can see that they are also not the new names. What TensorFlow, Beam, Docker, Airflow, Kubernetes, and blockchain. They are not the new names. We are familiar with these names. Or maybe we are familiar with these technologies, but till now or few years back, I mean, couple of years back, they were just in the hands of researchers and development groups. Now they are being they are playing roles in the industry. As it's always the case, I mean, industry is when it comes to the development of or the research of the technologies, industry uses it when it is being developed by their own R&Ds or by the academic world. But when it comes to being into the real business, it takes a while. It has to have some kind of a maturity so that it can be used in the industry for their business needs, for their business requirements, for creating the more profits to them. It's always the case. So here, when we talk about the TensorFlow, it is a robust, scalable ecosystem of resources, tools, and libraries, allowing them to create and deploy powerful machine learning tools and enhancing the quality of analysis and results in business predictions. I mean, you can think in academic community and everyone, students and all the researchers, they keep talking about the TensorFlow. So it's basically that an ecosystem with different tools and libraries. Then comes the Beam. It's being developed by the Apache. Apache Beam offers a compact API layout to create sophisticated parallel data processing pipelines through various execution engines. Apache Software Foundation developed these tools for big data quite a few years back, but it is now being used, slowly emerging and getting into the industry for their use. Then comes the Docker, is one of the tools for the big data that makes the development, deployment, and running of container applications simpler. Containers help developers stack an application with all of the components they need, such as libraries and other dependencies. So these are also being there in the research community, but now is being used, started penetrating to the industry. Then comes to the Apache Airflow, is a process management and scheduling system for the management of data pipelines. Airflow utilizes job workflows made up of directed acyclic graphs. The workflow makes it easy to manage, validate, and versions a large amount of data. Again, it is all about managing data, processing data, how well we can process the data, how well we can use different tools and techniques at one point part of the platform, or in a quickest way, without much of a complication. So it is those kinds of things. I mean, one can also think that they are being used in terms of what you call is the automation, where much of things can be done in much easier and not having too much of dirty work to be done, which initially was being done by what you call is by the people. Kubernetes is one of the open source tools for big data development, developed by Google for vendor agnostic cluster and container management. It offers a platform for the automation and deployment, escalation, and execution of container systems through host clusters. And the last one here is the blockchain. Is a big data technology. We are probably one of the most popular being talked about. Blockchain. Bitcoin is a big data technology that carries a unique data safe feature in the digital Bitcoin currency. Well, Bitcoin currency, when we talk about it, it still has some controversial things, but not getting into that. We just have to focus on the technology. I'm sorry, which cannot be deleted or modified after the fact is written. It's highly secured environment and an outstanding option for numerous big data applications in various industries like banking, finance, insurance, medical, and retail, just to name a few. So these are the emerging big data technologies. They are going to capture some for few years in the coming days. I would say in the coming few years, they will be much more sought and talked about it. And they will be widely used and then probably mature, and then something new will come. Now comes is the challenges. As you can see, it's image and text data, ethics, privacy, security, authenticity, consistency. Well, ethics, privacy, it's always when it comes to the big data technologies or data analytics or data science, there have been much bigger problems when it comes to the ethics. How the data has to be used, who is using the data for what kind of purpose, it's always a big question. So these are the challenges, and I would say they are not challenges from the technical point of view. In most cases, they are mostly the policy challenges, how to design the policy, how to take care of those kinds of issues. Privacy, yes, definitely, it's a big problem. I don't need to talk much about it. We all know how our phone numbers and information, once it is being put, it spreads, and then we start getting all those phone calls for each and everything and whatnot. I mean, privacy is a big issue. Once you accept certain application, when you start using an application and fill up the information, how it is being used, who is using, where it is going, it's a big problem. Privacy and security, one can combine it, and it can be used it can be thought about in a different way as well. Authenticity. When we are talking in the world of social media, how authentic the data we have it, how much somebody is putting in information or typing in information, how much we can trust that, and in the past, I mean, I'm sure the processing has to take care of many aspects of it. One is that how much can we trust? How much can we believe that people, what the trend is going? Is it a real trend, or it's just a hype? All sorts of things are there. When it comes to the consistency, yes, how we can take care of or how to deal with the consistency. I mean, right now something is there, and especially these things are becoming a big challenges when we are using the social media, especially the social media and those kinds of platforms for extracting the information or trying to find out those kinds of things. Where the mood swing, where people are not consistent, where a lot of reasons for, I would say, just there for having an inconsistency, and how to take care of those kinds of issues. These are still very big challenges. Not much of we have concrete answers to that. And now coming to the first one, but in the last, image and text data. Image and text data from a technical point of view is still a huge challenge. I can give an example where I was working on my own for an IBM project, and it was like in medical imaging. There is a big problem is of annotation. If you wanted to have a application developed for diagnostics of certain kind of disease using, say, ultrasound data or CT data or MR data, you need to have some kind of a information that what that disease looks like when we are looking at a particular image, say MRI or CT or ultrasound. Well, you need someone, an expert who can really sit and who can really do an annotation. I was thinking that can we do something automatically, because also getting those kinds of images is a huge problem. But when we look at it, those images, so many different varieties of those images are there into the web. So say, for example, if I wanted to classify between using X-ray images for lung cancer versus the TB. So I need a huge amount of data from different set of people, from different countries, from different patients. It's practically impossible. Can I use some kind of a big data technology or kind of a concept which allows me to have that amount of data and also an annotated data? So that kind of things are always a big challenge, as how you are extracting the features from an image which can match up when something is something different, some different in the sense, of course it's an X-ray image, but not that image which has been taken by, say, one machine, or it is from a different country person. So people from India or from Asian countries or from African countries, do they have the similarities? Do they have the differences? Can we bring and can we build up a platform which extracts the information from the images available over web, and they can be how can I have an information from those images to build up an application which can classify based on the images whether a patient has a TB or has a lung cancer. These are still very huge problems. One can think about it. I tried to build up a small application and try to use that kind of a concept. But I must admit that it was not a very big success to me in a given reasonable amount, in a small amount of time. But from my own experience, yes, I can talk about that. This image is using image from a big data point of view is a huge challenge, because how to extract, you cannot just one cannot just play with the statistical tool, because images are not numbers. One has to look into get into the numbers. One has to extract the features. How to extract the features, the best feature which can be extracted and put into the numbers. All sorts of things are there which puts the challenges. Now it comes to the just extract the information from the given set of images without any other inputs, or without any tag, or without any idea what that image is talking about. Can we extract an information from there? Now comes the how can we merge the image and the text data? What are the similarities from different images coming to the different text? How they are being related? It's all sorts of problems are there. Image data and text data, they are still a big challenge, especially in the social media. They are still a huge challenge. People are trying to put lots of images. They can have different meanings. They can have a different sense of interpretations. How to deal with that? How to build an applications which can take care of any specific applications? That these are all huge challenges. Computer vision, image processing, they took care of a lot of things in the past, and they are still working on it. But when it comes to processing images and text data in terms of big data, is a new challenge. It's a huge problem, and that's where a lot of effort is, and scientific and engineering and research is going on, and it's a big challenge. So here comes this. Thank you very much. I hope I'm able to communicate some kind of a message through this talk. And here I'm for questions and questions to take the questions from the audience. And in case if it is somebody wants to write and have in detail some kind of an information required about any technology which I have talked just now, you can just send me an email. Also, I would like to say that the images presented in this presentation and the slides, they are being taken from the various resources from the web. I don't have any claim over them. And so thank you very much. Thanks a lot.
Thank you, professors. Thank you, professors, for this was really a interesting session. I thank Professor Niyogi for chairing this session.
Yogi has left, Laksha?
Yes, sir, that's what
Then you can
we
thank
can
all the
see in the
speakers.
screen.
Then
Yes.
you can thank all the speakers.
Thank you, professors. I think Professor Niyogi has joined again. Sir?
Okay, then let him conclude. Professor Niyogi, can you hear me? He is muted. Please unmute.
I think he is not there, sir.
Okay, then Professor Andres, Professor Niyogi, and Professor Santosh Singh, I thank you all. See you then. I thought Niyogi can be here for concluding it. Probably he is having some problem and left the place. So I thank everyone on behalf of him. Thank you.
Thank you so much and have a good day. Goodbye.
Yeah. Hope that one day we will meet in Manipal or Delhi.
Yes, I'm looking forward to that. Goodbye.
So okay, so see all of you.
He is here. Okay. Yeah, please, Niyogi, you want to say something?
So, so Dr. Santos told no that he's here. I mean, or he has gone.
No, he has left.
He has left. No? So
yeah, he has a meeting.
If there are no other questions, or if there are questions, they can ask that address.
Yeah, we can use his email.
And they can address to him, and so it's nice that so we could make it. No, that that in spite of COVID, no, that he could make it. So Professor Andes, that so I extend my heartfelt thanks for joining the session, and
thank you so much.
So and see you later. Okay.
Goodbye.
Bye. So I'm just closing the session.
Okay.
Okay.
Then we'll go ahead with the next session. It seems Professor Lahiri is with us.
There is no voice in this.
Yeah, you bring him in.
Yeah, there is no voice. Yeah.
Yeah.
Am I audible?
Yeah. Sure. So you want to continue with your lecture without recorded talk? Like to deliver live talk?
Deliver live.
Okay, please.
Okay.
1 minute. Aksha, please introduce him and let us welcome him for delivering invited talk.
Yes, sir. Yes, sir. So in this session, we have with us Professor Somdev Lahiri from Pandit Deen Dayal Energy University, Gujarat. His areas of interest are microeconomic theory, individual and social group choice, decision-making theory, game theory. Today, he will be talking about game theory for decision-making under ambiguity. I now request Professor Prasad to chair this session. Over to you, sir.
Yeah, thank you. Professor Somdev Lahiri, I welcome you again, and please, now another half an hour is for you.
Can you see the slides? There are.
No, you'll have to share.
Yeah. Can you see it now?
Yeah, no.
Still not being able to see it?
Yeah, we can see.
Okay. Thank you very much. So this is the title of my presentation. That is game theory for decision making under ambiguity. Decision making under ambiguity is a kind of uncertainty that is different from what we are all generally used to, okay? Because most of the time, what we are really talking about is risk, where the probabilities, are known. Ambiguity is a situation where even the probabilities are underlying the uncertainty is not known, and that has to be estimated by some procedure as well. Now, this kind of research area actually began historically back with Keynes, but became popular after Daniel Ellsberg developed it in his PhD thesis. So I am trying to extend that analysis a little bit now, okay? So the problem of decision making under uncertainty, okay? So there's a decision maker, he has to choose an act from a non-empty finite set of acts. That's S0. And there's a non-empty finite set S of future states of nature, exactly one of which is going to be realized. The decision maker is unaware of the state of nature that's going to be realized at the time he has to choose an act. And this payoff function of the decision maker is pi, as defined out here, Cartesian product of the set of acts and the state of nature to the payoffs are assigned as real numbers. So they don't only depend on the acts chosen by the decision maker, but also on the state of nature that's going to be realized at a future date. Now, we are dealing with uncertainty, and as I mentioned, estimation of probabilities. So this is indeed linked with statistics in a way, from the point of view of decision making. But its relation to matrices are that this can be easily represented as the payoffs of the decision maker can be easily represented in terms of a matrix where the rows are the acts and the columns correspond to the states of nature. Examples of these are interactive decision making, which is so for some positive integer r, a set of r distinct decision makers different from the decision maker from DM r decision maker, each of whom has a non-empty finite strategy set. So the strategy set of the ith decision maker is Si, and S is the combination of the strategies chosen by the other decision makers. As far as the decision maker we are concerned with, what the other decision makers are going to choose, it's unknown, and it's just as good as some hypothetical player called nature or chance choosing it. So so our decision maker's problem is one where he has to choose an act based on the kind of probabilities with which the other decision makers choose their strategies, which for him is just nothing but a state of nature. Okay. The next example is that of parametric prices. In this kind of situation, our decision maker is participating in a market where the state of nature is a price or an ensemble of prices over which the decision maker has no influence. So the payoff received by the decision maker depends not only on his own act, but also on the prices that are realized. And in this case, the prices are being realized by interaction in the market. And as far as the decision maker is concerned, it could be just as well, God choosing the prices for him, but he's got to estimate those prices. Okay. Now, so in formal terms, the first assumption is there is a representative decision maker called chance who chooses the state of nature from the finite non-empty set S. Even at this point, we are departing from the conventional literature of decision making under uncertainty, whereas generally assumed that somebody called nature chooses the state of nature, the state of nature field. We begin with the analysis with the assumption that the person responsible or the group of persons responsible for, or whatever be responsible for the choice of the state of nature need not be, it could be a collection of individuals or it could be an individual, okay? So it really doesn't matter, okay? It's just, it's just that our decision maker does not know the probabilities. And the second assumption is the decision maker is an expected payoff maximizer whose interest in chance is merely concerned with eliciting the probabilities with which chance chooses each state of nature from S. As I mentioned, there are two kinds of probabilistic uncertainty the decision maker may face. The first you're already familiar with, that's decision making under risk. So I won't spend time on it because there's very little time. What we are concerned with out here is decision making under ambiguity. So there's a non-empty subset T of S, which could be S itself, okay? States of nature, over which the probability distribution is unknown to the decision maker. So he probably knows he knows the probabilities with which some states of nature may occur, but definitely not all the states, okay? And the states of nature whose probabilities he is not aware of is denoted by the set T. Now, here we introduce our solution. So he obviously has to estimate the values of P on T. The decision maker requires the following conjectural data. A payoff function for chance denoted by V, which is again, a payoff, S naught cross S to R. And a payoff function that chance conjectures about the decision maker. That's A, S naught cross S again to R, the reals. The point is, while this first one, this function P, is the conjecture by the decision maker about chance, about the payoff function of chance, this function A, is a conjecture by the decision maker about a conjecture that chance will be making about it. Okay, so it's 2 steps ahead. Okay, and so these are the 2 payoff functions out here. That again, now this P could be represented in terms of a matrix where the rows are the acts and the columns correspond to the states of nature. Now, in particular, this A could be pi or it may not be pi. Okay, so in particular, it's quite possible, though not necessarily, that A is equal to the true payoff function of the decision maker. The point is, the decision maker is concerned with the estimation of the unknown probabilities. So it's really not, he has to know the procedure or the way by which chance, views the problem and chooses the probabilities. So it began, there's this famous Ellsberg paradox, okay, on the basis of, of which a literature grew up in this direction. Now, generally, has been assumed that this B, the payoff function for chance, is actually minus A. So whatever is the gain for the decision maker is a loss for chance, okay? But we allow B to be anything, okay? Now, a probability distribution P on S chosen by chance is an Ellsberg solution if there exists a probability distribution Q on S naught. So P is a probability distribution on the states of nature, and Q is a probability distribution on the acts, satisfying the following properties. Now, the first thing is that P agrees with the known probabilities with which states of nature in S minus T, that is, are supposed to occur. So it must agree with the known probabilities. Okay. The second assumption is chance chooses a state of nature from T with positive probability only if it maximizes the expected payoff of chance given Q. So given the Q, the probability distribution that chance conjectures about the decision maker, he will assign positive probabilities only to those states of nature in T which maximize his expected payoff. And as far as the decision maker is concerned, he will choose an act with positive probability only if it maximizes the expected payoff of the decision maker given P. Okay, so the Ellsberg solution, the existence of such a solution has already been discussed in and got a proof of that already. It's not a very difficult proof. It's quite So once the Ellsberg solution has been obtained, the decision maker uses it to maximize its expected payoff or the payoff function phi, which may or may not be the same. The idea out here about the Ellsberg solution is, the determination of this P, this probability distribution, that's chosen by chance, where what P is, that payoff function of chance, and the payoff function that chance conjectures about the decision maker, okay, play a very important role. So essentially, this probability distribution P depends on A and B, and this Ellsberg solution is a minor modification of what one would call a mixed strategy Nash equilibrium. Okay, it's just a minor solution of that. So determining the unknown probabilities is a problem faced by the decision maker. According to the Ellsberg solution, the values of the unknown probabilities are the solution of a problem that the decision maker conjectures is faced by chance. As I mentioned, two very reasonable assumptions that are, I should say, may be involved. See, B is equal to -1. That's really what would lead to a kind of a two-person game, two-person zero-sum game or a constant sum game, is what has been the conventional method in the literature to decipher these probabilities. It's actually due to Gilboa and Schmeidler, Itzhak Gilboa and David Schmeidler. Okay, this solution. So it would be the max-min strategy. Okay. The other one, as a consequence of our allowing B to be different from A, which I would say is quite reasonable, is in a situation where the set of acts is equal to the set of states of nature. In that case, that is BST is equal to ATS. In other words, the payoff to chance, okay, if the decision maker chooses S and it chooses T, is the same as the payoff to the decision maker if the decision maker chooses T and it, that is chance, chooses S. So it's like a very symmetric situation. Okay. Now, number in this section 3, we have an example to illustrate the applicability of the Ellsberg solution for decision making under ambiguity. But we can always come back to that. Let me just tell you about, could somebody tell me how many minutes I have left for my talk? How much time do I have left for my talk? Because then I can discuss this.
Another 10 minutes.
Another?
10.
Okay. So let me tell you the work in progress. So what we've discovered now is what is known as the Ellsberg paradox. And there is a numerical example in section 3, which illustrates what the Ellsberg paradox is. This should actually be section 4, and this is work in progress. So, here what we do is something like a leader-follower type of game. Okay? The thing about the Ellsberg solution is the existence of an Ellsberg solution requires the use of a fixed point theorem argument. But this work in progress is something that tries to, can bypasses that and does it. So given a probability distribution Q over S naught and a probability distribution P over S, where P agrees with the known properties with which states of nature in S minus T are supposed to occur, let us denote by Q transpose AP the expected probability from the payoff function of matrix A. And this is the expected payoff of the decision maker. And Q transpose BP, which is going to be this, is the expected payoff of chance. Okay. So obviously we are using this kind of a matrix representation of A and B, where the rows correspond to acts and the columns correspond to states of nature. Now, given a probability distribution Q over S naught and a probability distribution P over S, where P agrees with the known properties with which states of nature, blah blah blah. We have these two sets QP. Now, QP is the set of best responses for the decision maker against P. Okay. Again, best responses in terms of mixed strategies. Okay. And PQ, okay, are the set of mixed strategies for chance against the strategy Q chosen by the decision maker. Where again, the best replies have to satisfy the probability that they agree with the known probabilities. Of the states of nature in S minus T. So QP is the best response set of the DM and P, decision maker, and P and PQ is the best response set of chance and Q. Now the probability distribution P star over S, which agrees with the known properties of S minus T, is said to be a DMS leader solution if there is a probability distribution Q star over S naught, okay, for which P star is the best reply against Q star, and Q star T AP star is greater than equal to Q transpose AP for all probability distributions Q over S naught and P belonging to PQ. In other words, what this is happening is the following. The decision maker, reasons this way, that if I choose a Q, then in response to that, chance will be choosing his best reply. Now, why don't I choose that particular Q so that if chance chooses a best reply against this particular Q, then that will maximize my expected payoff. Okay. So this is a result of an optimization problem. And if B is equal to minus A, that's a 2% zero sum game, this is nothing but the Max-Min solution. Okay. simply is the maximum solution. So this is the DMS leader solution. Okay. And there's another solution that's the decision makers follower solution, where the decision maker is reconciled to a more submissive role. He says, he reasons this way: if chance chooses Q, okay, if chance chooses Q, then I will choose a best reply against that. Then let me assume that chance is going to choose a Q, so that if I use a best response against that, then chance will be maximizing his own expected payoff. Okay, so this corresponds to a situation where the roles between the decision maker and the chance has been resolved. Now, once again, if B is equal to minus A, this is nothing but the min-max solution. And of course, the interesting question out here is, when is a DMS leader solution also a DMS follower solution? That's the first question. The second question is, when is a DMS follower solution also a DMS leader solution? That is, when do these two solutions, the first is the second and the second is the first? Now, obviously, we know from two-person zero-sum game theory that if B is equal to -1 and T is equal to S, the two solutions coincide. So the question is, are there any other? And this is the work in progress. I mean, we know that if B is equal to -A, then these two sets of solutions will coincide. So is there a larger class of sets A and B, matrices A and B, or payoff functions A and B, for which the two solutions will coincide, or one imply the other? Okay. We have, worked out for some classes of games, the solutions, and they seem to agree for those classes actually that are normally studied, like first of all, the matching pennies, or prisoner's dilemma, or for instance the coordination game. Okay? The coordination game, the two don't agree. Okay? But in matching pennies and prisoner's dilemma, the two do. Okay. So what are the other classes of games? I mean, games where this kind of coincidence, both agree. Now, with this being said, let me go back to the numerical example concerning the Ellsberg paradox that I have here. So the environment is a monopolistically competitive market for a branded product, basically a differentiated oligopoly, such as cola or salted biscuits. The different brands of such a product are usually similar, both by way of quality as well as price. When my time is up, please stop me. Okay. So however, brand loyalty allows for some flexibility in setting the price of any brand. So the decision maker is a profit maximizing firm manufacturing a particular brand of the product. Okay. And the pricing decision of the decision maker, that is what concerns us here. Okay. So assume that the number of brands in the market are not too many, say 2 to 4. It's an oligopoly type of situation. I think it's reasonable in the cola market and the biscuit market and things like that. It's FMCG, fast-moving consumer goods. Okay. Now the decision maker can choose between one of three acts: raising the price, lowering the price, or continuing with the same price. Now the profit of the decision maker depends on the overall reaction of other brands of the product or the future states of nature. And chance is actually a fictional or counterfactual representative of the other firms. Okay. So he conjures up a representative of other firms, okay? And for them, he has to, conjure up some kind of a price index. So chance chooses one of three possible future states of nature strategies, future states of nature or strategies. That's raise the price H, lower the price L, or continue with the same price, the same as DM, okay? And the DM cannot predict the strategy that chance will choose. However, due to prevailing economic situation, the decision maker believes that chance will choose to continue with the same price, that is M, with probability half. So there's 50% chance that there's a 50% probability that chance, that is his rivals, will increase their price or decrease their price, and a 50% chance that they will just continue with the same price. But he doesn't know exactly what is the probability with which chance will choose H or chance will choose L, that is his rivals will choose to raise their price or lower their price. Okay. So, A is the payoff matrix, the decision maker conjures the chance, conjectures that chance will conjecture as the payoff matrix of the decision maker. Okay. And so, if beta J is the probability chance chooses state of nature J, then we know beta 2 is equal to half. So essentially, the decision maker has to, given any beta, with beta 2 equal to half, he will choose his ANAC that maximizes his expected payoff. Now the decision maker conjectures a 3x3 payoff matrix P for chance. And what we have assumed out here is that B is equal to A transpose. Because in this market, it's natural for him to imagine that his rivals are, symmetrically placed, okay, as he is. So, he could, his conjecture is that the matrix P is equal to another 3x3 matrix, which is nothing but A transpose, okay? And according to the Ellsberg solution, chance will choose a state of nature from 1 and 3 with positive probability only if it maximizes the expected payoff of the latter from 1 and 3. Now, I won't go into the details of exactly what the calculation, because they're calculations and arithmetic. All that I'll tell you is the
Are you concluding now?
Sorry?
Are you in the concluding stage?
Yes, I am. So all that I'm saying is the first row of A is 100, 125 and 75. The second row is 100, 90, 80. And the third row is 150, 95 and 70. And the payoff matrix of B is equal to A transpose. And with this, it turns out that there are three possible solutions, Ellsberg solutions. And beta is equal to 0, half, half. That is, with probability half, chance chooses to lower the price, or beta is equal to half, half, 0. That is, chance chooses to raise the price with probability half. And the third one, where beta 1 is equal to 7 over 22 and beta 3 is equal to 15 over 22. That there's a probability 7 over 22 with which chance will increase the price, and 15 over 22 by which chance will reduce the price. And this seems to be most reasonable in the context of the problem we are discussing, because it is in spirit, it is in keeping with the spirit of the big picture. So with this time, thank you very much. If there are any questions, I shall be very happy to field. Okay.
Raksha, is there any question from audience?
No, sir. No, sir.
Oh, there is echo.
Pardon me?
No, when she said no once, 3 times it repeated. That's why.
Triple talaq. Don't mind, madam.
Okay, it was a good talk, useful for students, and it is wonderful. It has got some mathematics rigor also. Fine. Thanks a lot, Professor Lahari.
For my lectures yesterday.
Is it?
Yeah, I'm in the classroom actually.
Okay, thanks a lot. We'll be in touch.
Okay, namaste.
Namaste.
Bye-bye.
Thanks a lot, Professor. Thank you, Prasad sir, for chairing this session. And thank you all the link named as Professor George P.H. Stein Hall. Simultaneously, there will be an inaugural function for ICLA 2021. So interested participants, please join the link named as Professor C.R. Rao Hall. See you all tomorrow. Thank you.